Right. Hello, 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 everyone. Welcome in. We are hopping straight into it today. I'll give folks a minute to jump in here. Um, Hello. How we doing? Is my mic a little low? How's my sound quality? Hey, Michael. Welcome. Testing, testing. How do I sound? All right. I'm going to get closed captions turned on for y'all. Captions are live and available for those if they need it. Hey, Avo. Hey, Fangs. Hey, Quinn Sub. Alex. Hey, Solnix. Welcome to the stream. Yeah, how's my mic volume? Do I sound okay? Seems like it might be a little low, but let me know. Sound good? Okay. Hey, folks. I'm ready. Glad to hear it. Hey, JM, welcome to the stream. Thank you for the follow, KP2. Thank you for the follow, 0 Point Games, and Jeffrey Kithuku from Kenya. And am your daddy Memphis. Thank you. Oh, serious. Thank you so much. Woo! Thank you for the Prime sub. Yes. If you are an Amazon Prime member, please use your Prime sub on your favorite streamer. Absolutely does not have to be me. Could be anyone that you enjoy their content. It's free for you and it gives them a little extra cash. So, yeah, use your Prime sub if you have Amazon Prime on anybody at all. Make sure you spend that every month. And stop Jeff Bezos from going to space. Hey, James. Hey, Code Java, welcome. Hey, the real Randy. Austin, Texas. All right, folks. Yeah, welcome in. Welcome in. So, what are we doing today? Well, we are going to review a lot of the main concepts that were in the Front End Masters practical algorithm course that Leon assigned for this week. And thank you for the raid, Ian Douglas. Wow. Ian Douglas, great friend to the stream. Thank you so much. Oh, goodness. Another Prime sub. Thank you, Chelsea Harding. Wow. I'm feeling the love here today. Thank you all so much. I really appreciate it. Yeah. And Chelsea says, am I contributing to Bezos going to space with my non-Prime sub? Well, a lot of it does go, to the streamer. So, yeah. It's all right. He's still gonna have to sell his hat. All right. Hi, folks. Yeah. So Leon assigned the uh Ian, I believe I responded to your DM. I thought I responded to it. Let me know if you didn't get it, and I'll send you another message. Okay? Thank you. I really appreciate it. So Leon assigned the practical algorithms course. There was a lot of content in it, a lot of examples. But what we're going to do today is kind of just cover the main points, right? We're just going to cover like kind of the highlights, a little bit of a Cliff's Notes version. I would still recommend going through the whole thing. I think it's definitely valuable. But we are going to kind of do some review. If you've already gone through it, we're just going to kind of review some of the main points and go over a few of the like selected examples, probably not some of the most complicated ones, because that's not really the point, right? The point of learning data structures and algorithms is not to become an expert. It's not for us to become experts at data structures and algorithms. It's to give us that edge in interviews where we can speak to time complexity or sorting methods or, just kind of pull out a few little trivia facts here and there that can impress interviewers. So, I mean, if we really wanted to learn data structures and algorithms, you could make a career out of that, right? And then you could go and teach a computer science class. But again, that's not the goal here. So we're going to just kind of hit some main points. I'm going to ask some questions, see if folks can answer those questions. And yeah, hopefully just come out with a good sort of all around understanding of the concepts in that course. Oh, thank you, Leon. Thank you so much for the sub. I really appreciate it. Wow. Thank you so much, Leon. I appreciate your support in so many ways. Okay, let me see if I missed anything here from the folks coming in. Monomer asks, how long are we going today? So, not going to be a super long stream. We're not going to cover like the whole course again, right? I imagine we're probably going to go 3 to 4 hours. That's kind of been my standard lately. Also, it's a really beautiful day outside, and so I kind of want to go outside eventually. Oh, Ian Douglas, thank you for. Oh my goodness. Okay, wow. Ian Douglas, thank you for the 10 subs. If you just received a sub from Ian, please do thank them, and try out your new emotes. So if you got a sub, check out the emotes that you now have access to because they are adorable and I want to see people use them. Um, and thank you, Synesthesia. Thank you so much for the 200 bits. Wow, I can't even keep up with chat. Rascal says, so no 14-hour stream? Nah, we ain't doing that. Bruce Lewis says, going outside. I felt that. Yeah, it's nice to do now and then just so I don't become totally, vitamin D deficient. I'm already pretty, pasty. All right. Okay, so let's go ahead and get into it. So let's start out with kind of a little bit of a warm up. And I do have, so we're going to kind of alternate. I have a couple slides, but this is not going to be a slideshow. We're going to do a couple slides, and then we're also going to do we're going to review some code in Replit. A few of the examples from the course, we're going to review them directly in Replit. And yeah, just kind of have a little Q&A here. I'm scared of grass. I can't go outside. Okay. All right. So my first question for folks, let me get my notes pulled up here. All right. So my first question for folks, when we say the word algorithm, what is an algorithm? What do we mean? What do we mean when we say an algorithm? What does that mean? Yeah, I'm not just going to be talking at you. I'm going to be asking you to answer questions. How hard is that? Invisifam says baking bread. Yeah. So it's a finite amount of steps to solve a problem, a bunch of steps to achieve an outcome. Yeah, absolutely. And yeah, and it could be a function, right? It could be a function. That's a lot of the times what we are talking about when we're looking at algorithms in JavaScript is some kind of a function. But in general, just the word algorithm is talking about a series of steps that we might use in order to accomplish a goal, solve a problem, something like that. Yeah, exactly. And so when we look at algorithms in coding, um, we're looking, at a series of steps to accomplish some kind of output in general. We take an input, we do a bunch of steps on it, and then we come out with an output of some kind. Now, depending on how complex those sets of instructions are, how complex that algorithm might be, it might take a long time to solve. And there's a lot of factors that go into that. The types of methods that we use, um, how much data we're passing in, how many transformations we're doing on that data, all that sort of thing. And so, what do we call it when we want to think about how long an algorithm might take to accomplish, or um, um, how many operations it can perform in a certain length of time? What do we call that in official terms? What's the vocab word for that? Time complexity. Yeah, time complexity. Exactly. And so time complexity, the official definition is how many primitive operations are executed, um, and both within a period of time, with respect to the input size and with respect to it being the worst case scenario. So we'll talk about that a little bit more in a minute. So um, and what do we call it when yeah, time complexity is one thing, right? We want to think about how long it's going to take, and then we may also want to consider how much space that algorithm will occupy while it's executing. So for example, if I'm doing an algorithm that's looping 1,000 times, and each time it loops, it creates a separate array, and it's doing something with those arrays. Well, then you have suddenly you have 1,000 arrays. And so, what do we call that when we want to consider how much space that algorithm is going to occupy? This is a pretty easy one. Yeah, it's space complexity, right? Yeah. So we think about time complexity and we think about space complexity. So the practical algorithms course really doesn't spend a lot of time on space complexity. However, it's still something that you should know is a thing, right? They're kind of a pair: time complexity, space complexity. Um, Thank you so much. Wow, a level 4 hype train. Thank you so much. I don't know that I think that's probably only happened like one other time on my channel. So thank you again, everyone, for all your contributions. I really appreciate it. Thank you so much. Um, okay, so time complexity and space complexity. Now, when we talk about time complexity specifically, spaceship complexity. I wish that would be cool, but no. When we talk about time complexity, um, we don't think about it in terms of like, okay, I have an algorithm and its time complexity is that it takes 30 seconds to run. Now that's not something you're going to hear, right? You're not going to hear like, yes, this is, this algorithm that I've written here, it takes 30 seconds to run. Or this algorithm here, takes 10 seconds to run. So it's better. Now, why don't we think about time complexity in terms of units of time? Why don't we do that? That would be easy, right? You run it, you time how long it takes, and you say the time complexity of this algorithm is 30 seconds or 10 seconds or 5 milliseconds, right? Yeah, what are some reasons why we don't talk in those terms? Yeah, okay, so yeah, machines vary, right? um if you know if you have like a 4090 GPU and versus somebody who's using a netbook from 2005, it's probably gonna take there's gonna be a time difference, right? An execution time. Yeah, some people use potatoes, others use quantum machines. Exactly. Yeah, executing this on a research supercomputer like the one at my university campus is going to run faster than it would on my machine, right? And so, yeah, some other factors could be environment where you're running it. In a sort of a cloud execution environment, locally. Yeah, all sorts of things that would go into that. What language you're running it in? Yeah, it could be the same steps, but executed in a different language, which some languages are more efficient at some things than others, C versus Python or whatever. Yeah. Too many, yeah. And in general, what we're saying here is that there are too many extraneous variables or outside factors that we don't know and we can't control. And we can't predict either. And so, what we use instead is a different type of more general notation that kind of gives us a feel for how long something's going to take and allows us to compare different algorithms in a more general sense. And so, what do we call that? What is the notation that we use when we're comparing algorithms in this general sense? Yeah, right. It's called Big O. Yeah, it's called Big O notation. Yeah. Biggie O, yes. Big O notation, indeed. Yeah, and what Big O notation does is, like I said, it just allows us to compare these in a general sense. Um, and I'm going to switch to slides here just to kind of show you some common Big O notations. And I like looking at graphs and I like looking at visualizations. And so I really liked that there was a graph included with the front end master's course. And so I snipped it and I put it here in some slides. Unfortunately, it's kind of blurry, but hopefully you'll still be able to see it. So let me switch here. All right. So yeah, these are some common Big O notations visualized. And um, one thing I do want to include, let me just drag something else onto here. Let me see if I can grab this. All right, way to go. I'm assembling slides on the fly. Look at me go. All right, that's going to be behind my head. That's all right. We'll just drag it up here. Yeah, we need the title. Perfect. Okay. So these are not uh, these are not like the entirety of all the notations we could possibly have, but this is just an example of some of these notations and how they compare to each other. So the line down here, the horizontal line, is what we would call constant notation. So no matter how many inputs we shove into this algorithm, no matter how, whether I have an array of one or an array of um, you know a bajillion, is that it will, the execution time will always stay constant. It will not change. And so this is kind of like our baseline here. And then the next one up is O log of n. And I don't know about you, but I did not have the best time with math in elementary school, high school, and college. So I just want to take a quick poll. So how many folks? So if you felt like you were, if you enjoyed math and felt like you were good at math in say like high school or high school or college, you didn't go to college, that's fine. If you felt like just in general you enjoy math and you're good at math, type yes in chat, and if not, type no. I'm a no, but I'm just kind of curious of the mix. I could do a poll, but I'm lazy. Yes, but I forget. Small smooth right? Big no. Big no notation. Ah. Yes, but I don't understand anything. Okay, all right. It's an interesting mix. Yeah, I was just genuinely curious about that. I was sort of before burning out around university time and failing a bunch of my classes. Yeah, and I think university level math has a way of doing that, kind of sucking the joy out of everything. Um, it's a stretch to call it a joy, but it's interesting. Yeah, and so yeah, I was. For those of you who don't know, I was apparently a glutton for punishment, and I decided, even though I did not enjoy math in elementary school and high school, um, I decided to be an actuarial science major in college, which involves a ton of financial math. And so, yeah, that was not entirely enjoyable. But the main thing that stuck with me is I know what a graph of log n is supposed to look like. And so, um, Rahit asks, just finished with class 26, and Leon mentioned to watch your stream about APIs to learn more direct. I have a ton of streams on APIs. I'm not quite sure which one you might be referencing, but yeah, a lot of my streams use APIs. I would recommend maybe the Field Guide to Aliens or the Doggo Generator. And you can find those by going to my YouTube channel. So do exclamation point YouTube in chat if you want my YouTube channel. So go there and search for Field Guide to Aliens, Doggo Generator, or Pokemon Pet Checker. All three of those I think would be good. Yeah. And so yeah, if you're not super comfortable with math, looking at these functions might seem a little bit daunting. But it's really, we're not necessarily performing like any sort of, we're not performing these sort of algebraic sort of or operations really. We're just sort of learning these different time complexities and how to apply them to various standard things that we've already been doing, right? um, and so, for example, here we talked about constant time, and then the next one up is O log of n, and we notice that this one starts out pretty steep, right? This red line starts out pretty steep, and then it kind of tapers off as our inputs. Now that this horizontal line here, as our inputs get larger and larger, it kind of tapers off. And there could be a variety of reasons for that, but generally what we're talking about when we see something with a complexity of log n is that as you are performing more operations, you're splitting those inputs out into smaller and smaller chunks. And hopefully we can get this far today. We'll see an example of that in something like uh, well, basically sort of an operation where you take an input, and each time you loop, you break it out into smaller and smaller chunks, so you're splitting in half each time. And so each time you split it, when you loop back through that next chunk, it's half the size it used to be, and so it takes half the time to chunk it down. Um, and so then next we have square root of n, and then the linear time that we have here, O of n, simply means that as our inputs get larger, our time complexity grows at an equal rate. So we'll have some examples of what kind of algorithms could be called linear, but in general, like let's say we were doing uh, an operation on every single element in an array, and um, as that array grows by one, then it has to go through one more element in the array. And so our time complexity grows by that much. Yeah. And so, and then as we get into like quadratic and exponential, we can basically just keep going forever and ever. Um, and then eventually, this O n of n here is really just, basically a vertical line, which is not something that's probably not an algorithm you would want to implement at scale. So is that not O of 1? No, O of 1 is down here. See where the gray line is? Yeah. O of 1 is constant. Because here, n refers to basically the size of our input. And so it's kind of like on a graph where the slope is, the steeper the slope, the higher that number is in front of the x. This can vary, right? This can be larger and larger. However, a constant is always going to be the same. So 0 of 1 is constant. It will never change no matter how big our inputs get. Maybe if we want to make a computer super slow. Yeah. And another one is n log n. Yep. And we'll actually hopefully see an example of n log n a little bit later, um, which is our merge sort. Yeah, merge sort is n log n. It's slower than linear time, so it's slower than O of n, but faster than quadratic time. So it's between this purple line here and this blue line. Yeah. Okay. So I found this graph really helpful to kind of visualize these various things. And also this little mini graph here helps us understand the vocab words for each of these common designations. So constant is O of 1, logarithmic is O log n, linear is O of n, quadratic is O of n squared, and exponential is where uh, is basically k to the n, where n is the exponent. So it could be infinitely large depending on depending on the size of our input. Shen Prime says, when is it appropriate to really worry about any of this? I feel like in everyday web development, it doesn't really make much difference. Yeah, that's a great question. So at scale, once you start implementing things at scale for thousands or tens of thousands of users, it's gonna start to matter. Because think about this. Okay, think about this. If I'm a user and I go to your app and I click on just a button that's supposed to take me to the next page, and it takes 10 seconds or even a noticeable amount of time for that page to load, then I'm probably not going to be using your app for very long. And so if your algorithms get overwhelmed as the number of inputs grow, then users aren't going to want to use your stuff. And so you're going to need to start thinking about time and space complexity as you start to develop things at scale, which is why employers want to know that you know about this sort of thing in an interview, so that you can at least have some mindfulness when you're developing to say like, yeah, I can optimize things so that they are usable for a lot of people. Okay, so let's keep going. Yeah, great questions. So why is the number in front of the n not taken into account? Yeah, so just for the general notation, um, we don't really we don't use the number in front of the n to compare algorithms in a general sense. Yeah. Okay. So, and somebody mentioned earlier, I didn't answer the question right away because it was something I wanted to ask now. So, on this graph, we can see that some methods, should we care if some of these methods, so like for example, n to the nth, is actually, it seems to be really fast when our inputs are small. It's much faster than O of n, right? So should we, and it's faster than constant time. All of these are faster than constant time at small inputs. So should we care if some of these methods are faster with small data sets but slower at scale? So if our data is really small, should we be using O to the n of n? What do we think? So like I'm talking small, small, small scale. Just what do we think? Should we care at small scale that some of these are faster? Should we optimize? Yeah, right. No, we shouldn't. We shouldn't. So what we should do at small scale is focusing on readability. So focusing on readability. Yeah, the time difference is going to be minuscule, and you're going to save time on refactoring and development if you can make it readable instead. Yeah, and that was the same answer that the instructor gave in the practical algorithms course. And so I want to be sure to emphasize that. Um, of course you can practice this stuff for interviews, but developing at small scale, you probably don't need to, you shouldn't optimize until you start getting to large scale and you find that you have to, things start slowing down. You're like, oh, crud. Okay. All right. So as we're looking at these various types of notations, can we think of some examples of constant operations? So by constant, remember, we mean that no matter how big the input gets, it will uh, the time complexity will not grow. The time complexity stays the same no matter how, if, whether we have one input or a billion. Um, how can we think of some constant operations? Yeah, yeah. Reading the length of an array. Um, Yep. Looking up array values. Yeah. Reading an element from an array. Absolutely. Reading the properties of an object in general. Yeah. 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 And when we're talking about arrays, also things like array.pop and array.push. So when we talk about referencing something at a certain point in an array, at a certain index in an array, or in general, reading the properties of an object. Um, why is that true? Why is that true? Why, if I read something from index 10 in an array, does it take essentially the same, why is it that constant, even if I'm reading it from, index a gajillion in an array? Any guesses? Oh, I'm sorry. We got a stretch there too. So while you're thinking, I'm going to stretch. Sorry, I didn't see that. Oof. Yeah, I mean, it's the same number of steps to get the value. Oh, hydrate. Okay. I'll hydrate again. Yeah, and all the elements are indexed because every in JavaScript everything is an object, right? And so these objects have properties. And so if we do, all the index, all the as we add things to an array that's matched to that index, and the same with the properties. So like the length of the array, it's stored in the property. Yeah, it's everything's an object, so it's property of the object. We have all these indexes stored. They're already there. It's just a lookup. It's saying, hey, go to this index and grab the value. Yeah, and Jazz puts it a great way there. It uses the index as an offset to point to that element. It doesn't, it's not iterating through the whole array. Exactly. Yeah. Yep. Okay, good. Perfect. Um, and also another thing that's constant is like mathematical operations. You know, one plus one, one plus a million is going to take the same amount of time. Yeah. Uh, all right. So we talked about a couple of array operations like pop, was it push and pop. Those are, yeah, those are the two opposites of each other, and those are when we add something or take something off the end of an array. What about if we manipulate the beginning of the array? What about shift or unshift? So that's when we take something and we add or remove it from the beginning of the array. It's the same thing, right? Is it? Yeah, folks are saying it's actually linear. It's actually linear. Right. Yeah. Now why? Yeah. Why does that make a difference? Why if I it's this I'm eh, with push and pop, I'm putting something on, taking it off the end, and with shift unshift, I'm putting something on, taking it off the beginning. What's the difference? Yeah, we gotta with shift unshift, we gotta take everything in the array and shift it over by one index. Exactly. Yep, you got to do this. You got to, and that's why I like the, you know, finally that the shift unshift um, method names is actually starting to make sense to me with that actually, you know, now understanding that part of it. It's like, oh yeah, it's called shift unshift because it when you want to add or remove anything, you got to shift everything over. Shuffle tax, yeah. Exactly. So that actually helped me with like why the heck that method is called, you know, um, shift unshift, and with the ones at the end, push and pop. And I like to think of like with pop, it's like you're flicking something, you know, flicking something off the end, just boop, flicking something off the end, and then you know push, you're pushing that index out by one. Always thought the method names were weird. Yeah, I'm not saying they make perfect sense, but now that we understand what's actually happening, it does make it a little more clear. So yeah, unshift. Um, Now I don't generally use shift and unshift in my you know day to day life. But unshift isn't that when you are at isn't that the one where you're adding one to the beginning? Does anybody use shift and unshift? Like, and I remember the teacher in the algorithms course asked the exact same question. She was like, "Does anybody actually use this?" Which I thought was amazing. Yeah, shift is when you sorry, unshift is when you're adding something, and then shift is taking it off the beginning. No worries from the piece. Yeah, it's the opposite of what you think, and that's what I always have to think of every single time. Use them a few times, probably don't need to. Yeah, I mean, I'm sure there's use cases, otherwise they wouldn't exist. Somebody's got a use case out there, but yeah. Okay, so we've kind of brainstormed a few potential operations and what their complexity. You know, we looked at some constant. Okay, let's go ahead and look at the complexity of a few common operations. Let me make sure y'all can see that. It's not behind my head. Good deal. Okay. Let's look at the complexity of a few common operations. Um, and a couple of them we talked about, right? So just like running a basic statement, doing a value lookup on an array, object, or variable. And you know, in JavaScript, everything's an object, right? So all these properties are, you know, going to just already be available for us. Um, Now, when we start talking about some additional ones like O log n, we said, okay, so log is essentially, we know that that graph starts out kind of steep, but then eases off as we go out into infinity. And so, kind of like I mentioned earlier, that could be a loop that cuts the problem in half with every single iteration. So maybe we're narrowing down the amount of values that it has to go through every single time that loop repeats. So we're eliminating data. Maybe I like to think of like a some kind of a loop on a like maybe on a sorted array that's looking at like greater than less than like a binary search or something. It's just checking to see if a value is greater than or less than, and finally narrowing down into the final result. And so that could be a loop that cuts the problem in half with every iteration. And then if we look at constant, uh, uh, not constant time, linear time, with linear, a good example of that is just your standard, like a standard for loop, right? We're looping through the values in an array. And the reason, let's just flip back to our graph here real quick. The reason why the data input, as the data input grows, the time complexity grows at the same rate. Is just as we loop through it, there each time we add one item to our input, we add 1 unit of time to our complexity because one more item to loop through. Yeah, so that's a loop. Um, Now things start to get weird when we start. Bobby says log n sounds like some dude named Logan trying to come up with the username. Yeah. uh, oh, Elchi, thank you so much for the Prime sub. Yes, spend. Thank you so much for spending Jeff Bezos's money without. You don't have to spend any of your own. You're just spending Jeff Bezos's money and stopping him from getting to space again so quickly. So thank you, much appreciated. The Scotch hat, let's get weird. Yeah, exactly. We're getting weird. So when we start thinking about, this is what's called quadratic. We start thinking about these. This is when we could, qualify this with. So let me say that again. So when we start nesting our loops, we're going to start to get into this exponential notation. Sorry. So double nested loops are going to be considered quadratic because each time we add one input, so like say one value to our array, if we have nested loops, we're going to be adding one loop to the outside and one loop to the inside, right? So the way those nested loops work is that we start on the outside loop and then we go to the inside loop and we loop through every element in the array, and then we iterate by one on the outside loop. We go back and we loop through every element in the inside array, and then one more on the outside. So every single time we add one input to our array, we're adding n squared number of loops to the totality of the algorithm. And so it's the same thing for triple nested loops. And so, this is just one example. There's other things that could be classified as this, but if you're looking for, a quick reference on what each of these complexities, examples for each of these complexities, I think this is a great little graph. Oh, log n makes me think of a certain X-Man with claws that cuts lots of things in half. Yeah. And so a quick rule of thumb for calculating the complexity of multiple types of operations. Essentially, if a loop is involved, you're going to be multiplying it by n. Not true every time, but that's just something she mentioned in the course. And there are other notations aside from big O, right? We always think of big O when we think of algorithms, but there are actually other notations out there. There's notations for average scenarios. I don't know if maybe that's big like A or something like that. I don't know. And best case scenarios. So it's important not to forget that when we talk about big O notation, we always want to think about the worst case. So if we have a group of multiple operations in the same algorithm, we want to look at what is the worst case for all of those. And if three of them are constant and one is quadratic, then we say that the algorithm is quadratic because that's the worst case. Is there ever a moment where we would prefer quadratic over constant if a constant solution exists? I think we probably want to go with the constant. If you get the correct output, right? It has to be the correct output. And so I assume that, if a constant solution does exist, that's probably what we'd want to use. But, again, that's not a blanket statement. Is there an n exponential complexity in code? Yeah, there is. It's right here. And it, yeah, it could be, potentially it could be pretty much infinite. That at some point you're going to get close to a vertical line at scale. And so that's not what you want. But yes, that is one of the notations. And that's, this exponential notation here. All right. I don't know that I have a good example of an exponential. If somebody else does, you can feel free to share it. I mean, yeah, you could get into that with some, like with brute force. Yeah. Some of your brute force solutions where it checks every single, or where it has, completely naive, with no restrictions, and checks every single input every single time, no matter how large that input might be, and does multiple layers of operations. Like, I think when you start getting into like really deep um, data structures that you're checking through every single time, that could get into exponential. All right. Let's see. Talked about array methods. Okay, good deal. All right. So we talked about kind of this basic notation, um, and how we can kind of classify this stuff, and quantify this stuff a little bit, and compare time complexities. Um, Another thing we want to talk about is loops inside recursion. Maybe, yeah. Another thing we want to talk about is then optimizing. So if we have something that we know is going to maybe run a little bit slowly at scale, we can do something called optimization, and where that can help us reduce the complexity of repeated operations. And one of the methods that the instructor shared with us in the practical algorithms course was something called caching. So can anybody tell me, what do we mean when we say we're going to optimize something using caching? Or in general, what do we mean? What do we mean by the word cache? Yeah, yeah, we're storing something for future use, right? Remembering, storing. Squirrels, so squirrels, gather up acorns in the fall, and then they cache them for winter. Exactly, they're storing something for cache me outside, yeah. They're storing something for use, for future use. And just for reference, cache is spelled CACHE, so it's not spelled like cash money. It's spelled like CACHE. Yeah, yeah, it's a stash. Exactly. You can think about it that way. You can think about it as stashing too, if you prefer. Um, and so in the algorithms course, um, the instructor gave several examples of how we can use caching to help optimize our algorithms when they're executed repeatedly. Now, if you think about this at scale, that could be pretty useful, right? If you have an algorithm that is going to maybe generate like a finite set of results over time. So, um, you know, I don't know, maybe 100 unique results or something like that. What you can do, but it's going to be executed several thousand times. You don't necessarily want to recalculate that same result every single time you run the algorithm, because that's a waste of time. It's a waste of resources and time. What you should do instead is calculate it, is calculate it like for the first time, store that result in a cache, and then you can reference that cache. So when the same value is passed in later, hey, give me the same value again. You don't re-execute the algorithm. You just go up and grab it out of the cache and just return it. Yeah, and it's a trade-off. It's exchanging time for space. And the instructor is pretty clear about that, is that yeah, if you are going to have something that's going to return potentially a gajillion different possible results, Do you want to cache every single one of those? Do you want to have an array that's, a million values long? Is that too much space? I don't know. These are the kind of, considerations that you need to make at scale. But for this particular technique, if you maybe say have a finite amount of possible results, again, it's a trade-off. It's the kind of thing that you talk about in meetings, right? And when you're developing a large scale app. Uh, Red Style says, "What course?" It is the front end masters um, practical algorithms course, and it's free. You don't have to pay anything. You can view the first part of it for free, and so that's what we are reviewing here today. So yeah, free options are the best options, and so that's what we're talking about today. The operation still has to be done though, at least once for each user. Yeah, it does. The operation still has to be performed at least once, but then if that same operation is then asked, if that same input is then passed in again, at least the second time, it'll just return immediately. Fewer clock cycles to grab that piece of data that you frequently use. Yeah, it could be. Yeah. And Rascal 2 there has posted a link to the course that we're reviewing. So if you're interested, I would highly suggest you check it out. I'm really just giving the Cliffs Notes version today. I'm only going to be going over a few of the many examples in that course. And so again, I would highly recommend it. All right. So in the course, the instructor talked about a specific type of caching, and that is called memoization, not memorization. I'm not having a speech difficulty. It's called memoization. So essentially, what we're doing is we're writing down the answer. We calculate the answer first, and then we write it down like a memo, and then we can reference that memo later if we see that same value passed in again. Just taking notes. Um, And so let's go ahead and look at an example in a Replit. Let me get it pulled up here. I told you it wasn't going to be all slides today. Okay, let's make sure we can see that. All right, how does that look? Do I need to zoom in? Is it okay? The word looked like a typo before? Yeah, it does. It does look like a typo, doesn't it? Looks good? Okay, a little bit of zoom. All right, let's see. I just want to make sure that we can still fit everything on the screen. Get rid of that for now. Okay, I think that looks okay. Good stuff. All right. Good. Awesome. Yeah, and essentially it's turning it into just it's take that's a great thing. That's a great summarization there, Solnix. So it's essentially taking an algorithm that would take longer if we were executing it every single time, and then when possible, it's turning it into a simple lookup. So a simple constant operation, like just looking up a property within an object. So we'll have our cache, which is an object, and if that value is in the cache, all we're doing is looking it up and returning it. So very much reducing the time complexity of repeated operations. Yeah. Okay. So let's look at what this is doing. So the first thing was just to write a function that takes an argument called n and multiplies it times 10. Now that's very simple. We know how to do that. We've created a function here called times 10, which takes in a number n and multiplies it times 10. Yay! Now what we're going to do is use an object to cache the results of the times 10 function. So each time we run it, if that value has not been seen before, we want to add it to the cache. So create a function that checks the value for n has been calculated before, and if the value for n has not been calculated, calculate and then save the result of the cache object. Okay, so the first thing we do here is we start out by simply initializing our cache. Now, look carefully. Look carefully at where we are initializing this cache. Why is it the first thing that we do? Why is the very first thing we do say const cache equals an empty object? Why? Piece of shoot. I can tell you're trying to communicate, but I don't know what you're saying. What you're saying. Yeah. Why is this why is this numero uno? Why aren't we putting it inside of the function that we create? Okay, so we got some good guesses there. That it's really not a crazy reason. It's just because every time we run this function, we want that cache to stay accessible and available and not get reinitialized every single time. So, what do we call that when we have something outside of a function that we can keep accessing repeatedly and without it being reinitialized every single time? Yeah, it's global. Exactly. It's a global scoped variable, right? Now, is that best practice? No, it is not. And so after we do this one, we're going to see another way of, of doing the same thing that does not use global variables. Yeah, because global scopes are generally not recommended. Um, just because it can get messy. If everything's global, then things can get messy. Um, and especially if you're working in real production code, when you have a bunch of functions and a bunch of things happening at once, yeah, global can be messy. Um, yeah, global variable, exactly. So, but for now, just for example purposes, let's consider this global. We need encapsulation. Yeah, yeah, exactly. Global variables are against the notion of encapsulation. Yeah, and so we're going to see a way to maybe fix that problem a little bit here in a minute. But for now, just bear with me. Um, I have things that are global in my project, needs to change them. Yeah, when you get the chance, you can refactor that. Okay, so first we start out with our global cache. So this will remain every time we execute our function. This will remain accessible and it will remember the values that we put into it. So we create a function here called memo times 10, and we're passing in our value. So, an integer of some kind. And I just have a console log here just to better illustrate when I run this. It'll be a little bit more clear about what's happening. All right, so it takes in n, and the first thing it does and looks to see if that value is already in our cache. And then if it is, we console log that value found, and we return the previously calculated value at that index in the cache. And so once I run this, we'll see how that looks. Oh, older streams, yep, are on my YouTube channel. So follow that link, and that's where they all end up. All right, so if that value is in the cache at that particular index, then just return the value. No calculation needed. We just do a simple return statement at that location inside of the cache. However, if that value is not found, then we do a quick console log saying, hey, we're calculating, we're storing the result. And then the result essentially becomes the result of the times n function. So we just take that n value, multiply it by 10, store that result in the cache, and then return the result itself. Okay, so essentially we're saying, all right, this result wasn't in here before, but we're going to calculate it using our times n function up here. We're going to calculate that, call that function, calculate the result, store it in the cache at that particular index, and then return the result to the user. Because we don't want to forget, we do want to cache the result so that we can use it in the future, but we also still do need to return the result now to the user that requested it. So let's do a few of these. Just run. So you can see I have a bunch of different calls to this here. Um, Calling it for 9, 9, 8, 7, 6, 8, 8, 6, and 9. And several of these are repeated values. So let's run it and see what we get. Okay, so the first thing is just the execution of our times 10 function. We already know how that's going to work. So focus on the stuff here under task 2. All right, so initially, my first console log of the cache is empty. We haven't stored anything in it yet. And then the first time I execute this, I pass in 9 and I execute this function. It looks in the cache, there's nothing there. And so it goes straight to the else and it says, all right, calculate the result, store it in the cache, and return the result. So the result is 90. And now my cache has one value of 90. It's stored at index 9, and the calculated value is 90. And again, if I pass in 9 a second time, now it goes into this if statement. It says if n in cache, it's there. All right, the value is found. And it simply does a lookup in the cache and returns the result, no calculation. And then again, so now I pass in 8, it has to calculate it, it stores it. Now our cache has two values, the result for 8 and the result for 9. And we can see how this is going here, right? The next one I pass in 7, the result is 70, it stores it in the cache. 7, 8, 9 are now in there. I pass in 60, same thing. Our cache continues to grow of stored values. Now I go back and pass in 8 again. And now it looks in the cache. It says, oh, 8 is in there. Make sure you can see that. Yeah, you can. Good. 8 is in there. Value was found. It just returns that result of 80. And again, I pass in 6, returns 60. I pass in 9, returns 90. Okay, so does that make sense? Do we have questions on what this is doing or why we're doing it? Is it clicking a little bit? I hope we can see that why this might be I hope we can see that why this might be valuable to us, right? We can create essentially like a glossary of previous results and just reference that. And this, for this, it doesn't really matter all that much. It's a simple function, right? But imagine if we were doing some crazy, wild set of operations and you didn't want to do them every single time. If you had a really resource intensive operation, you could just store the result the first time and then never have to do it again. Yeah, you can turn a long operation into a short one if you need to repeat it. Yeah, exactly. Yeah, and factorials. Yep, factorials are one that's an example in the course itself. Factorials are a good one because they build on each other. Fibonacci, yeah. Yeah, and so a couple folks have mentioned this in operator. I thought that was interesting. I didn't really look into it, but I thought that's kind of neat. Is that you can just say, "Yep, if n is one of the keys, if n is one of the keys in our object. Remember, we have in an object we have key value pairs. Um, if n is one of the keys in our object, it can just look it up like that. That's neat. Is this how it saves images behind the hood on web browsers? I don't know. If anybody does know, feel free to speak up. But I mean, it could be one way. I'm sure. I'm sure there's all sorts of. So we know that there is a ton of caching that goes on um, in on web pages, right? There's a ton of caching. So the first time you visit a page, it might be kind of slow, but then it's going to store things. And then the next time you visit it, it's going to be faster because those things are literally cached. So it doesn't have to load really resource intensive stuff every single time. And you can clear your cache. You can clear cookies, you can clear caches, in Chrome and other browsers. And so yeah, caching is pretty common in general as a way to save time. And Rezon says, I deployed a caching server to cache courseware students were accessing at the rural charter school I was supporting with slow DS. Yeah, that's a great use case. If internet connections are slow and you have, let's say, a site with a ton of multimedia content, maybe if you can cache some of that so it doesn't have to download it every single time. Yeah, it's great. And Piece of Shoot says React even has its own hook specifically for memoization. Yeah, absolutely. Even with caching, Chrome takes half my RAM. Yeah, Chrome is a beast. Naomi, hooks are a concept that's specific to React. So definitely check out, some React tutorials if you want to learn more about hooks. Okay, so so somebody mentioned earlier about um, well, if we have this global variable here, this cache variable, why don't we just create another local scope so that we aren't dealing with a global variable, which is a no-no in terms of encapsulation and best practices. And so yeah, we can absolutely do that. We can create a a uh, a variable that is above the scope of our current function, so above the scope of this function, but below global scope. So remember, we can have different levels of scope, right? This is not something maybe we've thought about in a while, but yeah, scope can have different levels, and so our functions can have different levels of access to different variables depending on how high or low they are in the scope. And so yeah, we can do this. We can move this cache to someplace below global scope, but above the scope of our current function. And does anybody know the vocab term of what we might call that? If we were to sort of enclose this variable inside of a parent function and then have this memo times 10 be like a child function inside of that parent, what might we call that? Yeah, we call it closure. Yeah, that's a good vocab term. We call it closure. Now, I honestly don't remember. Does anybody recall? Is that something that we've talked about before? Like specifically closure. We did talk about that in 100 Devs, right? We talked about closure at some point, but it's been a long time, I think. That may have been when we were first talking about scope. Yeah, briefly, exactly, briefly. I think it was mentioned at some point. Yeah, it was kind of an offhand mention, but in this particular course, closure is used pretty heavily. So um, you heard about it from networking. Okay, yeah, if you're hearing people mentioning it in networking and in interview opportunities, then I think it's going to be an important thing to understand. Um, but yeah, it's okay if you don't remember it. It was not something we spent a lot of time on. However, the next example that we're going to do, we're going to use closure. It was like April, a lifetime ago. Yeah. Um, we're going to use closure to take this variable out of the global scope, but still make it so it persists with multiple executions of this memo times 10 function. It persists and it's accessible. But so it doesn't get reinitialized every single time we run this. So, but the first thing we're going to do is we're going to take a break for 5 minutes because that's what we like to do. At the top of every hour, we'll take a 5 minute break so that you can go, get a drink, use the restroom, let your dog out, whatever you got to do, um, and get up, shake out your wrists, and be healthy. And yeah, piece of shoe. That's right. It is in the bank. Yep, yep. It's in the bank. So it's important to understand. It's not necessarily something that you have to maybe be able to implement on the fly, although I'm sure it would be impressive. But you should know what it is and how and what it's for. Yeah. All right. So when we get back, we're going to implement closure on this particular example. And again, this is straight out of the course. So um, something that's good to know, I think. So yeah, when we get back, we're going to do that. And then, yeah, we'll do our closure. And then we'll go onward to recursion. Everybody's favorite thing, recursion, mine included. Ugh, yeah. So we're going to do a little bit of recursion, not a ton, but just enough to kind of hopefully make it a little bit less opaque. I know you like recursion, piece of shoot. Yeah, me not so much, but we still got to know it and we got to do it. So let's power through. All right. Thank you for the follow there, VN. Let's put 5 minutes on the clock. All right, reset that and start it. And I will see you all back here in 5 minutes. During the break, if you do have any questions, feel free to ask. And I will do my best to answer them when we come back. All right, folks, come on back. Come on back. Got about 10 seconds left in the break. Sorry, I normally notify sooner. Got distracted. Reddit. All right, I'm going to go ahead and stop the timer. Okay. And I'll turn my camera back on. There we go. And we're back. Good stuff. Okay. Um, so, Om Nom Yum asks, can someone explain closure again? Don't worry, we're going to do an example, and that'll probably make it a little bit more clear. Um, and Rascal did give a nice little explanation there as well. Okay, so let's open. Let's see, this is exercise one prompt. I'll make sure I get the right one. Let's do. Let's make sure I get the right one here. Sorry. Okay, let's look at this one. Yeah. All right. So this should look somewhat familiar. It's a lot of the elements are going to be exactly the same as the previous exercise that we looked at. All right. So again, we have our basic times 10 function, which multiplies an input times 10. Hooray. Now, what we see down here is going to look a little bit different. So let me move this a little bit down, this a little bit up. There we go. Okay. Now we're initializing our cache inside of a function called memoized closure. So we have this function called memoized closure. Okay. And we're declaring a cache inside of that. Now we might be wondering, okay, how does that work? Okay, well, let's keep going. And then after that, we have a return statement here that returns all of the same calculations that we did before, right? Checking the cache. If it's not in the cache, doing the calculation and then returning the result to, adding it to the cache and returning the result to the user. But all of that is now essentially inside of a return statement. So we have a function declaration. It's doing everything it used to do inside of a return statement. Okay. And then the last thing that we've added here is a new variable called memo closure times 10. And that is equal to the executed memoized closure function. Okay, so what we're doing is we're executing this memoized closure function, and assigning it to this variable here called memo closure times 10. Okay, so thinking carefully, what happens? What do I expect to get back when I execute? What do I expect to be returned when I execute this function called memoized closure? What is being returned to me? That's your hint. When I execute memoized closure, what is being returned? Yeah, a function is being returned. Not a value, just a function. Yeah, everything from this end statement onward, right? Make sure I get my brackets right here. Yeah, right there. Yeah. Everything from this function declaration onward is being returned when I call memoized closure. And now that is assigned to memo closure times 10. So what happens is essentially this now becomes a child of memoized closure. Interesting. So memo closure times 10 becomes a child of memoized closure because it contains this part. And now, Because of the rules of scope, if a child function is enclosed inside of a parent, that child has access to the variables of the parent function. So our memo closure times 10 function has access to the variables of the parent, in this case, the cache. So we execute memoize closure once, it initializes the cache once, and now every single time we call memo closure times 10, it can access that cache, and the cache is not reinitialized every single time. So the cache remains accessible and persists, and we can access it every single time, but it isn't global. It's encapsulated by the parent. And that's the beauty of closure. Hope that makes sense. So let's run it. Let's test that theory and make sure that it works. All right, I'm going to add a couple additional executions here. Yeah, so closure is important. It's a good thing to know. It's a great thing to pull out and say like, well, and somebody might ask, okay, how do we get, how can we get rid of global variables in code? Well, you could do like we could encapsulate those variables using closure, right? So that could be a great thing to pull out in an interview and say like, yeah, I know what this is. All right, so or they might ask you for an example of how we might use closure. In that case, you could say, well, if we have some global variables, we can simply, take those variables and close them in a parent function, and then have a child function within that parent that can then access those variables without them having to be global. All right, let me add a few more executions here. And do 10 there for the last one. And I want to console log the cache occasionally here. So let's do the console log of the cache. Console log, kind of like we did for the first one. Oh, I cannot spell. This is why I didn't hand type all these like live, because I am the master of typos. All right, let's run this and see what we get. Make sure it works. Yeah. All right. So we can see that the first time, we run it with 9, we've initialized our cache so it can put things in there, and it does the same thing it did before. It calculates the value, adds it to the cache. Second time we run it for 10, it's not in there, caches it, returns the calculated result, and the same until we get to passing 9 in again. That cache is still accessible because we're running a child function, which is able to look at the variables of its parent. And so we can just fetch it from the cache and return it. So it essentially does the same thing that the other implementation did with our global variables, except we are able to use better practices of when we're talking about scope. We're able to encapsulate those variables safely so that they can't possibly interfere with other functions down the line. Sensei says, man, that sounds like a very JavaScript thing to do. I don't know. Okay, so good question. For those of you that are familiar with other languages that are, similar to JavaScript or use similar concepts to JavaScript, is closure something that is used in other languages? I'm thinking like, I don't know, Python, C, etc. Console log cache in line 34. Yeah. Yep. We'll do that. I'll take it out of here so we don't get confused. Right, run it again. Yeah. So the reason now, why doesn't this work in line 34? I'll let you answer that. Why did we get an error? Why doesn't that work in line 34? Because we fixed, because this is because we fixed the encapsulation thing, right? That this cache is no longer global. It's enclosed within this memoized closure function. This cache variable is not accessible outside of this function. So as soon as we, try to access it outside of the function, like here, we can't because it's no longer global, which is a good thing. We don't want that. Yeah. So I'm glad we tried that. Yep, it only exists within the scope of the function itself, block scope. Yeah. Yeah. And yeah, we the reason we're encapsulating this in the first place is that if you are working with code that has, a ton of different functions on it, the more global variables you have, the more likely they are to interfere with each other. You might end up trying to access a variable you didn't intend to. Um, and yeah, it's best practice to try to encapsulate your variables where they are needed, where they're going to be referenced at any point that you can. Well, think about, so the question was, well, as soon as the function gets executed, shouldn't the cache get deleted? Well, which function are we actually executing here? We're executing memo closure times 10, right? The cache was declared in memoized closure. We are executing the child. So we only executed the parent once. Yeah, yeah. And Rascal answered the question that I asked earlier about, well, are closures just a JavaScript thing? This is only, do I only care about this if I'm using JavaScript? And Rascal says, no, Python has closures in them for sure. Same for Java, Rust, C Sharp, and probably a bunch of others. Yeah, it seems like a fairly universal concept. Yep. What's the difference between? I want to make sure I understand the question. What's the difference between the this keyword in an arrow function and a function declaration? So arrow syntax is fairly new as of 2015, I think, right? Um, and it's a slightly more efficient way of declaring functions. We can assign them directly to variables, and then reference those variables later. Right here. It also shows up in a few of the newer methods as well. I'm not sure if I answered your question. I think Rascal's been a programmer forever. Rascal is eternal. Rascal is forever. Yeah, and Rascal is a great resource. So, also, too, while we're talking about it, quick shout out to Rascal 2's Twitch channel. Right now, what they have been doing is they've been going through all of the past projects in 100 devs, and I mean all of them. And they've been turning them into React applications. So, if you want to learn more about React or how to convert things from not React to React, please subscribe to Rascal 2 on YouTube. They've been doing this for a couple weeks now. Yeah, and Tame Mister there just posted a direct link to their channel. Um, so please do check, give them a follow and check out their stuff if you want to get better at React. Yeah, and Rascal says they're done. They've taken every single project and reactified it, which is pretty amazing. Add Rascal to Stream Team. I mean, hey, if I had any say in that, they would be there. Unfortunately, I don't, but yeah. Oh, and Marshall says, okay, good. Yep. Marshall says one difference in an arrow function versus a regular function declaration is that it automatically binds the this from the scope where it is used. Yeah. So that may have better answered the question that the person asked before. Yeah. Okay. So, but going back to closure, does everybody understand what we did here? Do we have any questions on what we just did? So instead of having this cache be a global variable, we've moved it inside, right? And we're still doing the same operations. We're just making the cache so that it's only accessible where it's needed, which is in this child function memo closure times 10. Yeah, explaining this is so hard because you have to say the word this multiple times and it just becomes like word salad. Exactly. Okay, so again, this can be a good sort of an optimization trick that you could bust out in an interview to impress the interviewer. um, say like, well, we could get rid of some global variables using, even if you don't do it, even if you don't, like, you might be under pressure from your coding challenges, speed, and all that stuff. Even if you don't implement it, this could be one of those things where you say, yes, I'm declaring a global variable here. I know that's not best practice. Um, Instead, what we should do is, probably use a closure, and you could explain what a closure is. Yeah, but mate, so we're putting everything inside this parent function, memoize closure, and then we're taking everything in this return statement and we're assigning it to memo closure times 10. So memo closure becomes a child in the scope. When we're talking about scope, it becomes a child, and so it can reference variables passed down from the parent, including the cache. Yeah. Okay. Good stuff. All right, got a few more things. Well, lots of more things to cover. So I'm going to go ahead and move on. But definitely, you can access the slides from the course, and you can go to the instructor's Replit and play around with all these examples yourself. And I would highly recommend it. So add console logs, change the inputs. Do whatever you got to do to make it make sense. And I think probably during the next break, I'm going to see if I can grab the link to those slides, or if somebody else has it. That would be great, because the instructor does have a link to the slides, which then contains replets of all the code examples that they use. And all I did was just fork those so I could have them in my replit and, mess with them, make changes to them, that kind of thing. Yeah, and no, I'll try to get that for you. I don't have it right here on hand, but I do want to share that with you. So probably during the next break, I will, which is in about a half an hour. I'll find that link to the slides and I'll share it with you. Okay. All right. So I think there's one more example that they did, but it's just another iteration on the closure concept. So I think we're going to skip that one. And let's go on to recursion, because that's important to talk about. How are you passing an argument without defining it in the function? Well, we are. Um, we are, because remember, when I call memo closure times 10, this right here, assume this is what you're talking about. When I call this and I pass in 9, it's executing this right here, which is expecting an argument. It's expecting a number. This is what's executing. Remember, because we assigned memo closure times 10 to the return value of the parent. And the return value of the parent is this function declaration right here, expecting an argument n. And so now when I call memo closure times 10 and pass in 9, it goes straight into this function. It's expecting an argument of n, and so it executes just fine. Recursion. All right, let's go into recursion. All right, so first off, I'm going to go, let me just change this real quick. Change my screen back again. All right, we're going to talk for just a little bit, answer some more questions, do some more Q&A, and then we'll go into some more examples. So BSL, it is a defined parameter for the child function. It is. So if you once you have the link to the replit, I highly suggest that you mess around with it a little bit. It is. It's defined in the arrow function as a parameter for that arrow function. You'll see it. All right. So looking at recursion. Oh, and Hazel was last question. All right, last questions on this. Zosina, I'm going to link the replit after the next break. I don't want to link my replits. I want to link the instructor's replits so that you can fork them. I don't want to link my stuff. I want to link the stuff from the actual source so that the person who actually wrote the examples actually gets the credit versus me. This is not my stuff. I don't want to steal other people's work. So, all right. Hazel, last question on closure. Hazel says, is it impossible to access the cache from outside of the closure? Yeah, and you may not have been here when but we did try that a few minutes ago. We tried to see, can we access cache outside of that parent function, and we can't. And that is the point. That's what we want, right? We don't want stuff to be able to be accessed outside of where we need it, and that's called encapsulation. Yeah, so that's a good thing. All right. So first off, What is recursion? Just in general terms, I'm don't need anything specific or crazy technical. What is recursion? Yeah, that's the old joke there, Jazz. Yeah. Yeah. It's essentially a function calling itself at least once. Yeah, it could be called itself multiple times. Yeah, it's when a function calls itself at least once, right? It could be more than once. But yeah, it calls itself. I like that, Shells. It's a function that calls itself until it doesn't, right? Because a function that called itself perpetually, then that's an infinite loop, and we don't want that. So eventually, what you're going to have is you're going to have a function that calls itself repeatedly until a certain condition is met, and we call that the base case. And so that's what kicks us out. Just like how in a loop, you're always going to have some kind of an end game. You're always going to, whether that's a for loop and you reach the top limit of your counter, or a do while loop, which runs until a certain condition is met. It's just another way of looping, right? We have a function that calls itself repeatedly. And until that base case is reached. Yeah. And somebody mentioned something earlier. I don't know why people still learn recursion as the main rule is to always try to avoid it. Now, when you say things like, always or never in relation to coding, that can be a bit dangerous, right? I would highly suggest that you watch this course because the instructor is actually quite passionate about recursion and the value it can bring when you are, uh, optimizing learning algorithms. Yeah. And I wouldn't say it's true. I would say recursion can be sometimes difficult to implement for the first time, but it definitely serves its purpose. And sometimes recursion can be easier to implement than trying to nest, you know, a bajillion loops together, right? You could just have it recurse and call itself again and run that loop again rather than nesting infinitely deep loops for infinitely deep data structures. Yeah, absolutely. And the instructor of this algorithms course shares the same view is that recursion can be really useful when you have complex data structures that you don't know how deep they are beforehand, right? You don't know how complex they are beforehand. You just want your function to keep calling itself until the calculation is done because you don't know how many loops you're going to need beforehand. Yeah, it's the right tool for the job, right? And that's why we always say, that the words always and never are really dangerous to use in general. The words always and never are pretty dangerous to use because it's all about the right tool for the right job, and sometimes recursion is the right tool. um only a Sith yes, only a Sith deals in absolutes. To Yes, that is the perfect Star Wars quote for this moment. Yep. Most Yeah, exactly. Most of the time Sith deal in absolutes. Yep. Yeah. So we shouldn't ignore it just because it seems scary. We should learn how to implement it and maybe practice implementing it a little bit. Okay. All right. So when that function calls itself, uh, we start to get into manipulating the call stack a little bit. So um, in JavaScript, we have something called a call stack, where it's kind of like a queue or a line in which an order of operations in which things are executed. And so the three rules of the call stack, and I don't have a slide for this. I probably should have done, but I really like this is the instructor plays something that she calls the call stack game in the course, which I really like. And there's three rules to the game. So when a function is called, it gets pushed onto the call stack. Seems fairly obvious, right? You call a function and it goes into the line to be executed. Perfect. All right. And then we start executing that function body until another function is called. And then we return back to step one. So the new function now gets pushed onto the stack, superseding the original call. So then it starts executing that function body. So it puts the original one on hold, and it says, all right, we're doing this one now. Okay, we stopped doing the original one. Another function was called. Let's do this one now. And then And so now we can kind of see where recursion comes into play. So if a function starts to execute and then calls itself, the original execution is put on hold, it's pushed down the chain, and we call that same function again instead. And we keep calling and calling and calling, going down the chain until there are no more calls because we reach our base case, which should contain a return statement. So that's the other rule of the game, is that a return is reached. So when a return statement is reached, we pop the current function off the stack and go to the next one that was previously put on hold. So now we go back up the stack until finally we finished executing all the functions that we put on hold. First rule of call stack is you do not talk about call stack. Yeah, exactly. We're essentially, it's like it's kind of like we're somebody who's like chronically bad at time management, right? We start doing something and then, oh no, I have to do this other thing first. I'm going to put my first thing on hold and I'm going to do this thing instead. Oh, there's something else I have to do first before it. So it's like we're saying we have to keep doing these things before the next thing happens. So we keep putting the previous task on hold every single time. And so essentially we go down the call stack deep enough until eventually there's nothing more to do. And we reach a base case, we reach that return statement of some kind. And we can finally go back to all the things we put on hold and finish executing those. And so what we're doing then is we're passing our base case value back up the call stack until we finally have something to return to the user. Or you run out of RAM. Yeah. JavaScript looks like me. Well, it seems silly, but it's really the task that's being performed is actually similar to what's happening with a loop, right? So with a loop, think about like something like do while or a for loop. I mean, they can be you can translate between the two, and there actually is a great example of that in the course is translating between a for loop and a recursive loop. Is it's you're just iterating and you're spinning your wheels until you finally reach the case that you want, the result that you want, and then then that gets passed through and returned. Yeah, so the goal here is to just dive down the stack with repeated recursive calls until you finally reach that base case. And in general, what you're doing at each level in the recursion is you are, refining you're refining your data a little bit. So you might be iterating a counter, or I don't know, performing like you might be subdividing your data, which we'll see later when we talk about merge sort. You're going to be, subdividing at each level until you reach your base case, and then going back up the stack. Well, Lucas, so sometimes recursion is easier to implement than a loop. Um, and I would highly suggest, listening to some of the examples that are given in the course. I'm just giving you Cliff's notes here. But if you don't know the depth of your data structures beforehand, you might not be able to write a loop that's going to successfully encompass every single permutation of all the elements in your data structure. And instead, you can have your recursion, which can just keep going for a very long time until it meets all the criteria and passes it back up the stack. So that was the example I think the instructor gave, and I'm sure there's other examples out there. I'm not saying that you have to go out there and use recursion for everything, but it's important to not be afraid of it. So let's at least do some examples, see how it works. And so that way, when you encounter it, or when you come to a point where you do have to implement it, you can say, yep, I can do this, versus just being, oh, what's that doing? You know? Yeah, and like Rascal said, recursion is commonly shorter or easier to write. It is, yeah. It has less baggage than a loop because you just have your function, then you call itself again, and but it is very easy to get wrong. It can be very delicate. Yep, and it's not something you might understand fully today. You won't understand it fully today. I still don't. But we can look at some examples, see how it's done, and maybe it's something the next time you write a for loop or a loop of any kind, maybe you could see, could I make this recursive when you do a code wars? If you want to make it more compact, or just for funsies, you could say, all right, I did this with a for loop, but or another kind of loop. Could I do this with recursion as well? Okay, so There are angels in my room. Yeah, it's just a little mobile I have hanging off of my light. It was my grandmother's, so it's nice to have it there. Yeah, and that's right, Zena. The Scotch IO course. So the other course that Leon asked us to go through, which I'm sure you've done, right? I have an introduction stream to that course as well. So if you need some help getting started, um, definitely check out my stream for that. In Scotch IO, we learned how to solve a lot of simple problems with recursion tools. So if you want to more practice with recursion, better understanding, definitely check out the Scotch IO course as well. Okay, I had an example, a specific example that I wanted to do, and it's this one. All right. And at some point in this course, the instructor actually also does a conversion from loop to recursion. So if you want to see how they relate to each other. All right, let me switch my screen here. We'll go back. You don't have to stare at my face. We'll go back to an example. Okay. Yeah, and Rascal says it's much easier tackling the recursive nature after already figuring out the logic of whatever it is finished. Yeah, that could be easier too. Understanding the logic first before implementing recursion, yeah, it can be valuable. Okay, so let's look at this. So what this is doing is it's a function that is supposed to take individual string elements from an array. So here we have elements S, CR, T space COD, and a couple of smiley faces, very important. Um, and it's supposed to take each of those elements and join them with a string of, in this case, it's E, but it could be whatever we want, right? Essentially, in general terms, we want to take an array of string values, individual string values, and join them with an additional element at the end of each value in the array. So just to make sure we understand, what do we expect the results of this execution to be? Before I even run it, what do we expect the results of this execution to be? Again, we're taking each of these string values and adding this individual element to the end of each, concatenating them, and returning the result as a single string. So what do we expect to see here when we finish running it? If we don't know, that's fine. I can go ahead and run it and we can see what we get. But after we know the output, then we'll go through the methodology and see how it works. Yeah, exactly. It's going to be it's going to be a secret code. Yep. It's going to be a string that says secret code with two smiley faces. So let's run it. Yeah. Oh, and I have a couple extra console logs in there too. So, but the end result is this string right here that I've highlighted. I have console logs in there to illustrate what's happening. But yeah, so this is the end result. It's just going to say secret code with two smiley faces. Okay. And yeah, there's tons of other ways we could do this. We already know a ton about string operators and things that we could do instead. But just think about this in terms of learning how recursion works, and less about the specific, way it's being like why we're using it here. But this is more of just I think it's a good illustration of how recursion works because we can clearly see what's supposed to happen at each step. All right. So in here, we have a function called join elements, and that takes two arguments. It takes an array. In this case, it's this array right here, and a join string, in which case here it's E. So our array and our joiner string. And inside of here, now we have a second function called recurse. And this is where the recursion is actually going to happen. So inside of the recurse function, we're taking an index and the result so far. Okay, so let's dive into this and let's see what it's doing. All right, so the first thing it does is, oh, wait, actually, um, before I jump into that. So just looking at the two arguments, index and result so far. Where does that come from? Where are we getting this index and result so far? because that's not what we're passing in here, right? Here we're passing in the arguments to this function, join elements, array, and join string. That's what we're passing in here. But where does this come from? Yeah, spaghetti. It's not that this needs recursion. It's more about teaching what recursion is. This could be solved in a million other different ways. Yeah, it's line 14, right? The one that says don't forget why this is here. I wrote that note for myself, so I didn't forget to talk about it. Yeah. So let's think about what happens. Okay. So we call join elements. We pass in the array and the join string. This function starts executing. Now you might think it's going to go straight into the recurse here, but no, what it does, this is just declaring this function. What it does first is it goes down here and it calls recurse. So think about it. This function is defined here, but it's not being called yet. And so the first thing we have to do in order to make this work is call recurse and pass in the values it requires. So index and result so far. So here we pass in index of 0. We want to start at the beginning, and result so far, which is our empty string where we're going to be putting our output. So this function has a return value, and it's the result of the recursion function. Okay, so now that this has been called, we can actually go into it and start execution. All right, so it's been called. We can go into it now. Result so far, we take that and we add to it our input array. Again, this is in the parent, so we can access it. It's in the parent. It's within scope. We can access it. We say, all right, get the array at the index value that we passed in, which is 0. So what is that? That's S. And now I have a console log here to illustrate that. So we can see that that's the first thing. We're getting the first element in the array at index 0. Cool. All right, now we do a check to see if the index we are currently at, which is 0, is equal to the array's length minus 1, pretty standard. Then return the result. However, we are still at index 0, so we aren't going to return anything. We're going to go into the else, and we're going to call recurse again, incrementing the index by 1, taking our result so far, again, which is S, and adding our join string to it. So at this point right here, what would I see in result so far plus join string? What would that return? If I were to console log this, what would it be? Oh, thank you, Bowtie. What would it be? Result so far plus join string. Anybody else know? If you're completely confused, let me know and we'll go over it again. I'm not asking these questions for my own benefit. I'm making sure that folks are following with me. So if you're not following, that's okay. I can talk about what happened again. Yeah. It's going to be SE, right? Because result so far, join string. Now, what we're doing here is the second level of recursion. We're calling recurse again. And this time, we're passing in an index of 1 and a string of SE, right? Index of 1, a string of SE. Okay, so now we go back to the beginning because that's how the call stack works. We've called another function. All right, call stack's like, I'm going to stop what I'm doing right now and go into the next level. So recurse. Index is 1. Result so far is SE. Take result so far. Add the array value at the current index, which is CR. Console log that. We can see what we have here. SECR, we're at index 1. Check the array length again. We go straight to the else case and back into the recursion. Incrementing the index one more time. We're now at TCOD. And oh, sorry, yeah. So we take our existing strings SECR, add the E, and then we go into TCOD and do it again. We just keep recursing and going down the call stack until finally we reach the our index is going to equal array.length minus one. We've we've gone through each of the elements in this array, the S, the CR, the T, COD, the two smiley faces, and we have joined them with that E. And so we've reached the end of our array. If this was a for loop, we would have looped through the whole array, right? We're at the end. And so we reach this base case. We've reached this base case. So what do we do when we reach the base case? Well, we return the final result, and we return it going back up each level of the call stack. So we've recursed, let's see how many times, 1, 2, 3, 4 times. And now we just return that value at each level all the way back up until finally we reach the top level again, and our outer function is finally able to return the result of this function execution. Because remember, we started out executing this, but each time we went through, we went deeper down the call stack, and this function never finished executing. So finally, once we hit the base case where we're able to return, now we're able to return it all the way back up the call stack until finally our outer function is able to return the result. And that's somebody asked, well, what is this for? Well, yeah, this is because this is the function that we executed, right? We executed join elements, and it has a return value of recurse 0 empty string. And this recursion function wasn't allowed to stop until it had gone through the entire array and joined it with our join string, in this case, which was E. So it recursed 1, 2, 3, it looped around 1, 2, 3, 4 times until it was finally able to return a result of this execution. And then now our outer function is finally like, okay, now I can be done. I'm done. I'm going to return the result of this execution, which is secret code. Yeah. So the join element function ends when the base case is met. So not join elements, recurse. So recurse is our recursive function. Join elements is just the parent. So recurse ends when the base case is met, and it passes that return value all the way up the stack until it finally gets here. And then our outer function says, okay, I finally have a result for this that I can return. I'm going to stop executing now too. So E is base case. So our base case is this right here. The word, when I say base case, what I mean is the thing that stops the execution, or the thing that stops the recursion. So in this case, if this condition is met, there's no more recursion, right? It's not saying that, it's not calling itself again. It's just saying, all right, we have our final result. We want to return that. So in this case, the base case is when we have finished iterating through the entire array. So just like with a loop, our end case would be as soon as we reach the end of the array, right? And so that is the base case. Oh, is my chat command not working? I'm sorry. Let me try it again. There we go. Okay, there's the result of the chat command for you. Okay. So again, what we're doing is we are going through each index value of this array, repeatedly calling itself and iterating the index, while at the same time adding the string value at that index to our result, and also adding in our join value. So we can, again, we can look up here and see what's happening at each level. So we start out with just S, and then our next result set is secret or secret code, and then finally secret code is the end result. Yeah, it's the base case is the condition that needs to be met in order so it doesn't call itself anymore. Yeah, Zena, maybe I misunderstood your question. Let me read it again. Isn't the purpose of line 14 to call the recurse? Yeah, for the first time. Yes, it is. So Zena, maybe I misunderstood your question. If you want to ask it again, that would be fine. I thought you were referencing line 8. Yep. Line 14 invokes the recursive function for the first time, which starts the recursion until the conditions are met. The value is returned back up the call stack, and then returned to the parent function, and then displayed in the console. Yep. Okay, and this might not make sense yet, and that's okay. Feel free to keep asking questions. Exactly, Zena. That's it. Yes. So what's happening at line 8 is that after we hit that base case, we're already like 4 function calls deep, right? And so thinking about the rules of our call stack, the rules of our call stack is that every time it encounters a new function call, it puts the existing call on hold, and goes one deeper into the call stack. So it's got a queue. It's got a queue of all the previous executions that it still has to get through. And so we reach the base case. It ends the current execution, pops that off the call stack, goes to the next one. So it's passing it back up the chain until it can finally finish executing everything it's waiting on. So we've gone about 4 levels deep. We're returning that value all the way up through all the recursive calls, and then finally returning it to the parent. Yeah, it's like a bunch of plates in a sink. You got to wash the first one on top of the stack first. Yeah, just keep popping them off. Yep. Karova, I'm using Replit here. I mean, there's tons of different tools you can use. I'm using Replit here just because for the course that I'm referencing, that's what the instructor used. So I'm using Replit just because it's what was used for the course. All I'm thinking is pachinko. Um, it's there is, but there. Remember, there's like an order of. It's a call stack, right? So you can't just reach in anywhere into the stack and retrieve something. Um, the calls have to be executed in order and completed in order. Oh, but mate, I'm glad it clicked. Yeah, it's okay if you don't get it just yet. That's fine. Um, it's kind of difficult to wrap your head around sometimes. And so let's see. I think I have another example here. It is time for a break. So before we dive into another example, what I'm going to do is we'll go ahead and take our break. First in, last out. Yeah. We'll go ahead and take our break. And then when we come back, well, and during the break, I'm going to find for you the link to the slides, which contains all the replets for this. I would highly suggest that you, number one, do the course. And number two, look at all of the replit examples and mess with them yourself. We already know that's the best way to learn, right? The course that I'm referring to is the front end masters course that we were assigned for 100 devs. If you don't know what I'm talking about, exclamation point Leon in chat, in what you see in the top left corner of my screen there. But yeah, this was assigned for this week's homework. And so I'm just giving you cliff notes here. I would highly suggest that you look at the replets yourself, play with the code, add console logs, remove console logs, fork all those replets and mess with them on your own as well. Yeah, and this course that I'm referencing is completely free as well. So I will get you a link to the course and a link to the slides. So you have all this information to mess with too. Okay. Oh, and Jazzy Pants there pasted a link to the course, and during the break, I'll get you a link to the slides, which then links to all the replets. All right, let's go ahead and take our break. 5 minutes on the clock, and we will. And when we come back, we might do one more example of recursion, and then I really want to make sure that we get to the different types of sorts and that kind of thing as well. Those are really important to talk about. So um, I don't know. I got to think about what I want to spend my time on here for the last hour. But I'll think about that during the break. So 5 minutes on the clock. We'll start that, and I will get you those links as well. So much to learn. I know. Yep. That's why, again, we don't need to become data structures and algorithms masters, but we should have a level of wide familiarity with the concepts, the vocab words, the kind of things that you're going to want to be able to reference in interviews, even if you can't implement them on the fly. Okay. I'll see you back here in 5. I'll get those links for you.
I work as a
All right, folks, we got about a minute left in the break, so come on back when you're ready. I did paste the link to both the course and the slides with the replets embedded um, in the chat there, just a little bit above. Let me know if you need me to paste them again at any point. I'll probably spam them again here soon. First reference and with spaghetti. All right, 10 seconds left. I'm going to go ahead and stop the timer. Yeah, and Front End Masters is just the name of the website. Yeah, there's a ton of courses on there. There's plenty of free courses as well. So you shouldn't have to pay for any of these. The course that I linked in chat there, it is. Let me just pull it up real quick. The course that I linked in chat, I posted the link in chat. I'll also show it here on my screen. This course is completely free, and it's got a bunch of lessons about a bunch of different things. Again, please do this. Don't just take my Cliff Notes and run with it. Please do the course. I've tried to structure this as a complement to this course, right? Maybe touching on a few of the reviewing a few of the things that Bianca talked about, but it's a definitely good thing that you should do yourself. I'm happy I tuned in today and not after 4 hours deep in the other. Yeah. And what I like to do for those of you who might be new to my streams, what I like to do is I like to take this content, the content that we're assigned or the content that we're supposed to go through, and I like to talk about things that I feel the instructor or the presenter maybe didn't spend a lot of time on, that maybe they could spend more time on. Or maybe things that I thought they glossed over a little bit. And so a few of the things that we touched on already were things that I thought, like Clojure. Like she kind of assumes that you're familiar with Clojure. And I was like, no, we're not. And so that's why we spent a fair amount of time talking about it. With recursion, the instructor actually does spend quite a bit of time talking about recursion. And so I think we're going to please do watch the lessons on recursion. There's a whole section on recursion. I don't know if you can see that, but over on the left side, this course has a whole section on recursion. So please watch that. And this instructor is very passionate about it, so does a great job of explaining it in the call stack, playing the call stack game, which can be really valuable. So, oh, you're totally fine, Jazzy. No worries. Hold up, full stop. Which one is first? Primeagen versus this one? Well, this is the one that we were assigned in the follow-along materials. So Primeagen might have been first, but this one, yeah. Yeah, so this one is in the so this one's due Tuesday. So this is the one that's due most urgently. Yeah. Okay, and so one more time, I'll paste the link to the course. Definitely, if nothing else, watch the section on recursion. The instructor is very good at explaining it. There's the course again, and again, I'll paste the link to the slides as well, which have the replets embedded. And so what you can do, if you go into the slides, is you can navigate through. So looking at this recursion stuff, you can scroll through until you get to the replets, and then you can simply open these on Replit and fork them and fork them onto your own account and mess with the code yourself. So again, highly recommend that. I think for now, in the interest of time, we're going to move on to the next topic. We'll talk about sorts and things a little bit, types of sort, and types of search and sort stuff, like keywords that we should know for interviews. But again, she spends a lot of time on recursion on this. There's a whole section on it. So please do watch that and get more familiar with recursion as a concept. Okay. All right. So next, hang on. I think we're going to go to some slides again. Let me see. Reorient myself here where we're at. Okay, so the next thing we're going to talk about is ways to additional ways to optimize our algorithms and make them smarter. Um, so, in this case, we're going to talk about something called divide and conquer. So, has anybody heard of divide and conquer before? Even if you haven't heard divide and conquer, just by saying that, what do you think divide and conquer might refer to? Or as a concept, what do you think it might, what do you think divide and conquer might do outside of military tactics? Command and conquer, that's a video game. Good guess. Yeah, yeah, break a big problem into smaller bits. Divide and see if what you were looking for is there, and if not, then cut again. Yeah, yeah. And we saw a visual example of that a little earlier, right? So I'm going to switch my screen here again. Um, we saw a visual example of that earlier when we were looking at this graph, right? This O log n. Remember, we mentioned that what can cause something to be classified as O log n is when you keep executing, but each time you execute, the number of inputs that you're putting into it is divided by a certain fraction. So it might be half, it might be a third, it might be a quarter. You keep subdividing those inputs, so each time it executes, it keeps getting smaller. So it keeps getting it keeps taking less time to execute, right? And so it starts out pretty steep because the number of inputs is large, but then as you go along, it starts to trend toward more of a line because you keep subdividing your inputs into smaller and smaller packages. Exactly, Temporalis. Yeah. Got some fans of Command and Conquer out there. Okay, nice. Yeah. And so that is divide and conquer. So not command and conquer. Don't say that in an interview. That's a video game. But divide and conquer um, is uh, when you take a problem and you split it into smaller chunks until you finally get to what you're looking for, and then you may end up recombining. So in some cases you may end up recombining, and in other cases you may simply return whatever result you find. Or do call it command and conquer, but then use the correct one. Yeah. All right. So does anybody know an example of the? Can anybody give me an algorithmic example of the divide and conquer technique? I think I mentioned it before, but how to make a pigtail? Yeah, divide and conquer. Right. What's an algorithmic example of like a specific one, a named algorithm, an algorithm that we have a name for that might use divide and conquer to reach a goal of some kind? Yeah, binary search, right? Yeah, binary search. Um, that's a great example because when we do binary search, what we're doing is we're essentially taking a a sorted array. That's important. Binary search is a sorted array, smallest to largest, and we simply, we have the value we're looking for. You need to find X value, and you simply divide that array in half, and you say, okay, you know, is this value in this half? No, then toss it, get rid of it. And so now you have your smaller half, your leftover half. Is the value in here? Yes, it is. Okay. Or sorry, I shouldn't say it's. I shouldn't say is the value in here. Should say is our value less than the max or greater than the minimum, right? Less than max, greater than min. We don't know where it is yet, but we know it's in here somewhere because it fits within the range of the sorted values. So our value's in here. Okay, now we subdivide that again, two halves, and we check and say, okay, is the value that we're looking for less than the maximum of this half and greater than the minimum of this half? No? Okay, get rid of it. Now we have our one smaller half left. And again, and again, and again, and so until you finally have the index of exactly where that value is located in the array, and then you can return that value. So that's how we can perform a binary search. So an advantage of using binary search. So there's a couple different types of searches that we could do. One of the searches we could do is what's called a linear search, where we simply go through every single value in the array and check and see if it matches the value that we are looking for. That's perfectly valid. We could do that. I think Leon had an example of that. And this is also in the Scotch IO course. Leon said that's like if you went to a library and you went on, you just picked a bookshelf and you started going through and checking every single book. Now, if I go through and I'm checking every single book on that bookshelf, what do we think the time complexity of that operation would be? If I check every single book on the bookshelf and then I go to the next shelf and I check every single book on that shelf, what is the time complexity? Looking at these notations, what do we think the time complexity of that would be? Yeah, it's going to be linear, right? Because as we add more books, it takes longer to search through them. So, but if we try to use something like binary search instead, we just keep no matter how big our array is, we can simply keep subdividing it and searching smaller and smaller portions of it every single time. And so with a binary search, that complexity can be reduced all the way down to log of n. So we can see there's quite a sizable difference here between the time complexity of a linear search, and as our input size grows, we would much prefer to use a binary search. Okay, so great, awesome. Binary search sounds really cool and a good thing to use, especially when you have a very large array to look through. But what is, I mentioned this briefly, what is a potential pitfall of binary search? Should I just jump in and try to use binary search on every single array I encounter? Should I, is binary search something I should be using every single time for every single array? Yeah, in order for binary search to work correctly, in order to always be able to check the min-max values of each portion and see if our value is in there somewhere between that minimum and maximum, it has to be sorted first. So if you have a very large array that's unsorted, you gotta sort it first, and that could maybe be a trade-off that you don't want. Yeah. So you need to have a sorted array, and so the binary search is a great choice if your array is already pre-sorted, which could happen, right? You could have a pre-sorted array. Maybe it's sorted in a different function, or who knows? I don't know. It's or the outside system that you're getting it from has already pre-sorted it for you. That could very be possible. You what you're going to find on the job is that you're getting data from other systems all the time, whether it's a database or an additional application. It might come in pre-sorted, and you're like, "Yep, I'm going to binary search this thing." Um, and so, yeah, it can still be the right choice. It just depends on when it's the right tool for the job. So, if you're going to use binary search or mention binary search in an interview, you're going to want to be sure that you qualify that by saying, well, it's really the best choice at scale if the array is already sorted. Okay. And so let's look at a couple of quick examples. We'll look at a couple of quick examples of both linear search and of binary search and see how they are each implemented in different ways. All right. Okay, so in this case here, we have a linear search. And now there's no recursion here. Don't panic. It's pretty straightforward. It's just showing you what it's doing. So in this case, we're calling a linear search on this particular array right here, 2, 6, 7, 90, and 103. And the value we are searching for is 90. And so for linear search, we pass in list, which is our array, and item, which is the item that we are searching for. Our starting index is -1 initialized. This is just something that the instructor likes to do. That's how they like to initialize their indexes. Now we can simply call for each and check each item in our array. We should already be familiar with the for each method, and it's literally just checking every single item in the array for each list item at the current index. We simply compare that list item to the item that we passed in, and if it matches, set the return index to the index where we found it. So when I run this, what do we expect the output to be? What will this return value be? If I pass in this array and a search value of 90, what's my return value? Where did we find it? Yeah, exactly. My return value should be 3. So let's run it and make sure. Yeah, just as expected, the return value of 3. So it does work, right? It works. There's nothing wrong with it. It's not broken. It just may not be the best choice at a very large scale. Matt, what would you like me to repeat? Would you like me to explain what's happening here again? I want to make sure I understand your question. And again, there's other ways that we could do this, right? But in this case, what we're illustrating here is specifically linear search. So specifically the act of going through every single value in an array and comparing it to the value that we are passing in and seeing if they match. And if they do match, returning the index at which that value exists. Just the pseudocode? Okay, so let's look at it again. All right, so this function is expecting us to pass in an array and a value that we want to find. So in this case, we're passing in an array of numbers, and we want to find the index of where the number 90 is located in our array. Okay? So we pass that in. We basically just initialize an index value that we're going to be returning. And then we loop through the array that we passed in. We loop through it using the built-in for each method. This is something that's built in and you can use on any array that you want. For each item in our array, check if the current item, so let's say we start at 2, check if the current item is equal to the item that we are trying to find, in this case 90. So is 2 equal to 90? No, right? It's not. So we go to the next one. We start the for each again. Is 6 equal to 90? Nope. So it doesn't do anything inside this if statement. It just keeps executing the for each, checking each of the array values. So 7 equal to 90? Nope. It exits out of the if statement. Now we get to this one. Is 90 equal to 90? Yes, it is. So finally, this if statement gets to execute. And then all we do inside of here is we take the current index, so whatever index we're currently at, 0, 1, 2, 3, and set it equal to this index variable here, and then we return that value. Okay? So that's a linear search. Again, the concept is that we're simply taking an array and a value that we want to search for, and we're checking every single value in that array. This array could be 100 values long. For each would check every single one of them. Even if we can visibly see where the answer is, for each doesn't care. It's going to check every single one of them until it finds the one that matches. Bote says, why let index equal -1 and not 0? Well, so that's what this particular instructor, that's how they like to write their functions. That's just how they initialize. We could initialize let index as empty too. I mean, we could just do that. But they like to do this type of initialization for an index because if for some reason that value was never found, so let's just do this. Let's do this. I took the value 90 out and let's run it again. We get -1, right? Because that initial value is never overwritten. That initial value is never overwritten. And we know that when we're talking about arrays, what does -1 signify? When we're talking about arrays, what does an index of -1 signify? Just from our basic knowledge of general array notation and that sort of thing. What does -1 mean when we're talking about arrays? Yeah, it means nothing. It's not a valid index. So if you ever use a built-in array method and it returns -1, then you know that whatever you're looking for wasn't found or the index is invalid or whatever like that. So -1 does not exist. Yeah. And so that's why this is declared as -1, because if we don't find the value, that's what we want to return and clearly signify, yeah, this value does not exist anywhere in this array. Now, if I initialize this to 0, it's a nice starting index, right? And I run this, we get a result of 0, but 0 is a valid index. So I might think let's say I couldn't see this array for some reason, maybe it was being passed in from another system. I never get to see it. It's passed in as a variable or something like that. I don't get to see it. I might think, oh, wow, okay, it found 90 as the first element in this array. Cool, okay. And then I would do other things based on that result that are wrong. Yeah, so that's why they use -1 as their initializing value. I hope that makes sense. Yeah, and you would think that that this is where it found it, but it's that the value that's there is actually 2. Yeah. Okay. And Alpi says, what if returned current index? Well, that's what we're doing, right? We're assigning it to this variable here, and we're returning it. But I think what you're saying is, what if return current index? Yeah, that's fine. Let's do that. What do we think might happen? Well, let's run it. Uh-oh, we got an error. Why? Let's read the error. It says current index is not defined. Why doesn't this work? This is good. I'm glad we're having these discussions about how we build our functions. Math does not equal code. This is so different. Yeah. Yeah, you can't reach down in the scope. So think about the scope of this for each operation, right? The scope of this for each operation only extends into its own body. So so the scope of whatever we declare inside this for each, including the list item and current index values, is only valid inside of this scope. Okay? So if I try to access current index outside of this function body, outside of these brackets, it ain't going to work. It can't read it. Scope doesn't work that way. You can't reach down. You can only reach up in scope. And so if you're not familiar with scope, it's something that you really should kind of try to learn more about because it can be really valuable to understand when you start writing more complex programs, right? And so we kind of talked about scope a little bit earlier in terms of global scope and then parent scope. And now here we actually have basically, trying to access down to a child. So this for each is inside of this parent. And if the parent tries to reach down into the child scope, it can't do that because scope doesn't go that direction. So that's why we return index instead. Now, okay, follow-up question. But I set the value of index here. Why does it work? Why can I access index here in the parent? Why does that work? Why can I access index in the parent? Why can I access? Why does it know what index is? Run that again. Here we go. Yeah, where did we declare index? Again, it's yeah, scope is the general answer, but I'm looking for something a little bit more specific. Yeah, we declared it in the parent, right? We declared index up here, right? So index was declared in the parent function, and so therefore it recognizes it, and we can reference it. We can and also the child can access it as well because scope works. So scope works up, right? The child can reach up to the parent, use all of its variables just fine. It's a child, it can access a parent variable and assign a new value to it, and then we can return it down here in the parent. Yeah, we just reassigned it in the child. We didn't declare it in the child, we just reassigned it. Is this the closure thing? Kinda. Yeah, kinda. And it's the same principle, right? It's the same scope principle. The child can access the variables of the parent, and that's just a general property um, across JavaScript. You'll see it a lot. You see it in like classes and things. Yeah, object-oriented programming in general, encapsulation, is the general term. So yeah, it can be really useful when you're trying to create self-contained, functions and things. Okay, I hope that makes sense. So that was a linear search, right? That was a linear search. And let me return this to its previous state, functional state. All right, index is going to be -1, declare it like that. I'm going to add 90 back in here. And we'll run it again, make sure it's right. Yep, 3, good. Okay. What would happen if I included current index above in the parent function? It's a parameter variable. Well, I mean, you could technically access it, but here you don't need to. I wouldn't do that because we're using current index for a very specific purpose. It's being used for a specific limited purpose inside of this for each statement, only telling us the current index at which we are currently at inside of that loop. So for each is looping through, and we want to keep track of the current index. We don't need it anywhere else. It's not shouldn't really be used for anything else. And yeah, so that's we kind of just want it to be here, limited, out of scope. Yeah, right. And we only now keep in mind we only care about current index once it reaches the value that we want, right? We keep reassigning current index as we're looping through that array until finally it reaches the value that we want, and then we assign it to our return variable and pop it up. Yeah. And now you could streamline this. This could be much more compact, but it's more about demonstrating the concept than being perfectly, like a one-liner code wars solution, right? This could be very much more compact and streamlined, but we're not going to bother with that. Spaghetti, don't use var. Come on, Spaghetti, don't be like that. Use let and const. We can do it. Var is the old keyword. Let's use let and const. Okay, but we know what linear search is now. So let's look at an example of a different type of search, the second type of search that we talked about, called binary search. So what do we notice as we look at this particular array, the array that we're passing in here? What do we notice about it? Other than its length and the numbers it contains, what do we notice about this array? What do we see? Yes, it doesn't go like 1, 2, 3, 4, 5. There's jumps in between the numbers, but what else can we see about those numbers? It's sorted, yeah. Exactly. It's sorted. It's in order. So that tells us that another way we could tackle this is using a binary search. So let's look and see how we can apply that. Yeah, there's no decimals, it's integers, that kind of thing. But the main thing is that it is sorted. All right. Let's look at binary search then as an alt. And since it's sorted, we know, little light bulb goes off in your head, that we should be able to use binary search to tackle this as well. All right. So let's see how we can do that. So again, we are passing in the exact same array as before, passing the exact same array as before, and the exact same value that we're trying to find, which in this case is 90. Okay. So we're first going to declare a few variables, and they're using the var keyword here. I'm not going to change it. It's not going to hurt anything. So many vars. I know they're using var. I think in the live example, if you watch them do this like in the course, I think they use let instead. But all right, whatever. We'll just leave it for now. Spaghetti developer. Spaghetti developer's like, I told you so. Yeah. We'll leave it as is. All right. So binary search. We're setting a few variables. We have a min variable, which starts at 0. We have a max variable, which starts at list.length minus 1. So the length of our array minus 1. And we have a guess value. Okay. What are you seeing there? Bow tie. 90. No, that's 103, not 10. It's the array value. If it's too hard to see, I'm sorry. The values are 2, 6, 7, 90, and 103. So it is pre-sorted for us. Yeah. Okay. So let's look and see what's happening. We've set a min, we've set a max, we've set a guess. Okay. So we have a while loop here that says while min is less than or equal to max, we set our guess equal to math.floor min plus max divided by 2. Okay, so what do we think this is doing? Just turning our brains back to our basic, math operations. What do we think this is doing? It's taking min and max, dividing it by 2, and taking the floor. Yeah, exactly. Kim Possible coming in hot with the right answer in their first time chat. Nice, good job. Yeah, we're coming in with, so we're taking the min and the max, and essentially we're finding the average or the middle value. So it's not quite the average because we're taking the floor value. So one array could end up being larger than the other, but we're taking that and we're splitting it in half essentially. And the first thing we do is we check and see if we got it right on the first try. So we check and see, all right, if the value at the index of our guess inside of our array is equal to the item that we're searching for, then just return that. Yay, we got it right. Go us. However, if it's not, then we look and see, all right, is the value at that point smaller than our item? If it is, then our new min value is our guess plus 1. If it's not, then our new max value is our guess plus 1. So essentially all we're doing here is we're splitting that array in half, and we're checking to see, all right, since it's sorted, we can do this. We say, all right, if I'm searching for 90, I take this array, I split it in half, and I end up with 2 smaller arrays, one of 267 and the other of 9103. Or I guess maybe it's the other way around, but either way, I'm splitting it in half, as close to as half as I can be. And I'm checking to see if this value is in the first set. So I check and see, all right, is 90 less than 7? No. Okay. So 90 is not less than 7. Then I take my minimum and add it to my guess plus 1. So my new minimum is 8. All right, my new minimum is 8. My maximum is still list.length minus 1, so the end of my array. So I'm searching now between, or sorry, I'm searching, sorry, not 8. I'm searching now between um, uh, whatever index we're currently at, 0, 1, 2, 3, index 3 and index 4. And I check and see, all right, now is the value that I'm looking for 90? Yes, it is. Okay, I can return that and we exit the function. So let's run this and see how it works. Yeah. Again, we're just splitting this in half and we're checking each half to see if the value can be in there. And we can do that because it's a sorted array. So we always know that the min and the max are going to be accurate to what is inside of that range. So we split it, we check and see if it's in there. If it's not, we discard that. Check the other half. Yes, it's in there. All right. Subdivide again if needed and keep subdividing until we get to the specific index that we're looking for. So let's run. All right, and it found it at index 3. Now let's add some additional console logs so we can better illustrate what's happening. Okay, so I'm going to console log let's console log guess, min and max at the start of each loop. Okay, guess, min, and max. Let's see how that looks. Guess, min, max. Yeah, okay. So actually no, I'm gonna put this in a different order. Do this. Guess, min, guess, and max. All right, there we go. So the first time around, our min starts at 0, our max starts at 4, and so obviously our guess is going to be 2. So we split this array in half at 7, and in this case we say, all right, is the value at index 2, 0, 1, 2, less than 90? Yes, it is. Okay, good. So our min now becomes our guess plus 1. So our new index that we're looking at, in the next loop, our starting min is 3. 3, and our max remains 4. We never changed it, so our new guess is 3. And we are right on that line. So does this make sense? Are we following what's happening here? Again, we're just subdividing the array in half multiple times until we finally pinpoint exactly the index that we need. We can maybe make this a longer index, which might be easier to follow. More loops. Oops, 1, 1, 7, 8, 9, 10, 50. There we go. Okay. Still too quick. Only 2 loops. It's too fast. Binary search is too optimized, people. All right. 50, 60, 70. Here we go. It's too good. Okay, there we go. There's a few more loops. All right. So again, min starts at 0, max starts at 12. Our guess is 6 the first time. And we do the same checks as before. We essentially say, all right, the value at index 6 is 0, 1, 2, 3, 4, 5, 6, so 50. And we say, all right, is 50 less than 90? Yes, it is. So our new min is now guess plus 1. So our new min in the next loop is now 7. Our max is still 12. And our new guess is 9. So 12 plus 7 divided by 2, and the floor is 9. All right, so now we check 9. Whatever's in index 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, is 90 less than 80? Nope. So we increment let's see, hang on, 1, 2, 0, 1, 2, 3, 4, 5, 6, I'm counting wrong. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there we go. Uh, is 80 less than 90? Yes, it is. All right, so our min goes up by 1. Yeah, our min goes up by 1. And now our min is 10. Our max is 12. And our guess is 11. All right, so now it's a little different. So the value at 11 is actually too high. The value at index 11 is 101. Okay, so is 101 less than 90? No. So now for the first time we go to our else. So our max is reduced by 1 now. So on the very next loop, our min and our max become equal. So the while loop will stop running after this, and our current guess is equal to the item that we were looking for. Okay. I hope that helps. Rascal says, I counted wrong, me doing math in front of literally everyone. Yeah, no. No worries, Matt. Have a great evening. Okay, so I hope that makes sense what we're doing here. This is really helpful if you can try it yourself. But in this case, it was actually so efficient that I had to increase my array size quite a bit in order to increase the number of loops. You know, you saw how small that array was starting out. Look how much I had to increase it just to get a couple more loops in there, because it's so efficient at reducing reducing the size of the data that it has to look through each time. So much more efficient than linear, especially for an array of this size. So just for kicks, let's see, where's linear search? Let's put the same array into the linear search and see how long it takes. Well, it's going to take, actually, no, we don't have to. It's going to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 rounds to get to the same answer that our binary search did in like 4. Okay. How do we feel about this? Nice. Yeah. It is nice. Just remember that your data must be sorted first. Makes sense? Good. Okay. If it doesn't, you're allowed to say so. Good, good. Thank you for the follow, Haunting Human. All right. So again, if you have any questions, do feel free to ask, but we're going to keep kind of trucking along here a little bit. I want to get through at least the rest of the sort stuff. I'm new to binary. The list is part of it. Yeah, so this is simply the name of the parameter that we are passing in. Okay, I could name this whatever I wanted. I could name this sparkles. And as long as I kept that name consistent throughout the rest of my function, I could reference it as sparkles and my function would know exactly what I was trying to do. Really, this is just a shorthand for the array that I'm passing in. Okay, got it. What about line 10? Okay, line 10. All right, so if list bracket notation guess equals item. So you're asking about what this means? All right, so this is saying, all right, look inside of our array. And using bracket notation, what we're doing is we're passing in our guess that we made, which we set up right here. We're passing in our guess, and we're checking to see what value is at that guess. So if I make a guess here of, I don't know, 6, like we did here. In the first loop, we made a guess of 6. So we're going to go into this array, and using bracket notation, we're going to find the number that is at index 6 in our array. So 0, 1, 2, 3, 4, 5, 6. That's 50. And so the value that's going to be here is 50, and it's going to be comparing it to the item parameter that we passed in, which is 90. So that's what that equates to. Got it? The bracket got you? Yeah. And that's bracket notation. That's array notation. And so knowing what that is really useful as well. But you may not be used to seeing it with sort of two different names like this versus just like array and then an index value. So yeah, with bracket notation, you can the variable can have a sorry the array can have an alias name, and the index value itself can also be aliased. So that's what we've done here. Okay, good questions. Thank you for that. No worries, Kim Possible. Yeah. All right, so let's talk a little bit more about sorts. I have slides. Okay, let me slides. Okay, we'll be ready for the slides in just a second. So um, before we go into that, so talking about sorts, there are two types. So there's two types of comparison sorts. So what we're doing in comparison sorts is we're sorting values by comparing them against each other and checking to see if they're in the proper order. So the couple types of sorts that we can use are something called naive sorts and divide and conquer sorts. And we've already kind of talked about these, right? So a linear sort is basically pretty naive, right? It doesn't know anything about the values beforehand. It is essentially just um, looking through, seeing if the values are one value is larger than the other and swapping them around. And then another way we can do that is by divide and conquer. So in a divide and conquer sort, we're splitting our input value out into smaller and smaller chunks, and then sorting those chunks individually and then recombining them. So what is an example of a divide and conquer sort? It's an example of a divide and conquer sort. I guess a specific type of named sort that uses divide and conquer. Ooh, serious. Redeemed, create an AI generated image. Yeah, we can do that. Um, I have a channel point reward for using the Stable Diffusion AI image generator to generate an image of your choice. So yes, we can do that. Yeah, and Ruth Foot Motion says merge sort is an example. Yeah, so merge sort is an example of a divide and conquer sort. So let's look and see what excuse me. Let's look and see what a merge sort might look like. So what is merge sort and why is it divide and conquer? So look at the left graph for starters. So what merge sort does is it takes an unsorted array or unsorted input, unsorted list of numbers, and what it does first is it subdivides them, kind of like we did for our binary search, right? It keeps subdividing them more and more and more until it gets to the point where we only have individual values. Now the magic happens in the second half. So the subdividing is, yeah, okay, fine. We just subdivide this down into its individual values, and we haven't done anything with them yet. They are still in the original order that we started with, right? 38, 27, 43, 3, 9, 82, and 10. But when we start to recombine them, we take those individual values and we sort them in pairs. So we can see there 27 and 38, they've swapped places. 3 and 43, they swapped places. 9 and 82 swapped places, and 10 stands on its own. It's just passed through. And then at the next level, we do the same thing. We take our two pairs, which are coming in pre-sorted, and we sort them again so that they're in the proper order in the larger set. So now 3 comes first, followed by 27, 38, and 43. And then followed by 9, 10, and 82. So again, we're combining now in halves. Instead of breaking it apart, we're combining it back into halves. And then finally, we return the complete sorted array. Okay, so why is this better? Why is this better? Why do we want to do this? This seems wild, right? Why do we want to do this? Well, What's important is that you compare it to the alternative. So the other types of sorts that we could do instead are what's called naive sorts. Like we said before, they have no prior knowledge of anything that's in the array, and they're just going through and they're comparing every number against every other number. And you might have seen this in something called like bubble sorts, which is where you start at one end, you take the first value in the array, and you compare it to the value next to it. If it is larger, you swap those two values. And you keep bubbling that value up until you reach the point in the array where it is smaller than its neighbor. Smaller than its neighbor? All right, it stays there. It's there. Then you go to the next item and you do the same thing. You bubble it up through until it reaches the point where it stops, and then you go to the next one and you bubble it up through and then the next one. Now, so you can see that if we have an array of 100 values, you have to go through each one, check it against all of its neighbors, and then go to the next one, check it against all of its neighbors, and blah, 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 blah. So, what do we think the time complexity of something like bubble sort is going to be? Zena, no, I believe that the JavaScript sort function actually does quick sort, which is less, it's not a naive sort, I think. It's a divide and conquer sort, I believe. Yeah. Yeah, it's going to be, so something like a bubble sort is going to be quadratic because you can think of it like nested loops, right? You can think of it like nested loops. And there is actually there's a example of bubble sort that we can, I think I have an example of it. Yeah. And we can see why it's quadratic if we just look at one of them really quickly. If we look at bubble sort, we'll immediately be able to see why it is quadratic. Because we have nested loops. We're not gonna dig into this code, but just to why we're qualifying it as quadratic is that we actually have nested loops. We have to take that item, compare it against each of its neighbors, which is one loop, the inner loop, and then once we're done, go back to the next item, which is our outer loop, and then go back into the inner loop and compare it against all of its neighbors. And so when you have, we saw earlier that when you have nested loops, here, when you have double nested loops, that is a quadratic time complexity. Okay, so quadratic time complexity, not great. If we look at our graph here, we can see that quadratic complexity, it's not like logarithmic. It doesn't get better as time goes on. It gets worse. It gets worse. So kind of want to try to avoid that if we can at scale because it's going to be harder and harder to do as our arrays get larger and larger. So that's why instead we could maybe use something like a merge sort. And so looking at merge sort, we can see that the time complexity of these is n log n. Now that's a little different than what we've seen before, right? Um, but n log n is still much better than a quadratic. So n log n, where that fits on this graph, is not less than O of n, but better than quadratic. So it's somewhere in here. It's in this kind of in this wedge of space here. So it's a little worse than linear, but not as bad as quadratic. With the exception of constant, all of them get worse as time goes on. Yeah, just to vary. It's all about the degree of how worse it gets, right? That's what we're trying to factor for, is the degree of how bad it gets over time. And so we can reduce that badness just a little bit by using merge sort instead and kind of putting it in this slice of the pie right here. All right, now why do we classify merge sort as n log n? Well, here's a little breakdown of that. Again, this is in the slides. Because we have some constants, we're initializing some things. We're setting our, we're setting our split variables and that kind of thing. Those are all constants. We're initializing variables, setting things up like that. Creating our slices that we're going to slice our array into. But every single time we call our merge sort, we're splitting that array again, right? Just like with our binary search, we take this array and we subdivide it over and over and over again. And so we said earlier that binary search is going to be log n because each time we do the operations, it gets easier to look through. So that's log n. There's fewer operations over time. We're creating smaller and smaller chunks. However, unlike with binary, in the end, we have to put the thing back together, right? We split it apart and we do our sort operations against the little pieces, which makes it easier. But then we have to put the thing back together. And that, unfortunately, is a linear operation because at the very end, in the last step, we do have to sort through the entire array and get everything in the right order. So it is n log n, but still better than a naive sort like bubble sort. So it's an improvement. Okay, and there's other types of like naive sorts, such as like an insertion sort, which is when you create a new array and you look through the starter array and you put values into it in order. We talked about merge sort. There is, however, so we say that merge sort is better with time complexity of two starter arrays. We say that merge sort is the better choice. However, there is a good case in which you might want to use bubble sort, and that is if your array is already mostly sorted. So if your array is already mostly sorted, you just have a few values out of order, then you maybe don't want to go through all these steps to break it all the way down and build it back up. If you know you only have a few values out of order, you might as well do bubble sort, and it'll only swap the values that it needs to. And the instructor had a couple of things to say about merge sort in general. So they said, somebody asked, well, what is the best type of sort to use in like an interview session? Is merge sort something that in an interview you might want to try to implement? And they said, no. They were like, merge sort is probably going to be too complex for you to implement in an interview setting. However, you should definitely reference it. You should say, I'm going to use insertion sort or bubble sort or something like that to just to accomplish this task here in the interview setting. But for to better optimize this for time complexity, I should probably I would probably want to use merge sort, which has a complexity of n log n instead of this naive sort, which has a complexity of quadratic. I could make this more optimized using merge sort, and then you could explain what it does. Yeah, use the thing that works, and then mention the better way of doing it. Exactly. So mention the better way of doing it. Show that you understand what it is, what it's for, how it works, like this, and throw that out there as a nice little piece of trivia. And I think Leon mentioned too that another way you could do it is you could always do the brute force solution in the interview, and then go home and implement the merge sort, and then email the interviewer and be like, look, and I optimized it here with merge sort. Yeah. And so again, definitely look at the code um, in the slides. Look at the replit and look at the merge sort and see if you can dig into that. Bad code plus a little bragging about the optimal solution. Yeah, absolutely. In the interview, write the code that is going to serve you best, right? Write the code that you are confident about. Write the code that you've done before, that you've practiced, that has the least uncertainty for you. But know what these things are, right? The point is not that you can implement all this from memory. The point is that you know that these are possible, that you know that they are more efficient than the basic sorts, and that you can wow your interviewer with a little bit of vocab and trivia and explanation of that the optimal solution, you just aren't going to implement it right now. Yeah. And you might be amazing, right? You might be able to do this no problem, in which case go ahead. But again, do what is comfortable for you in the interview, but have knowledge of where it fits in the hierarchy of optimization, right? Understand that if I just do a bubble sort and a comparison, that it's going to be slower. You could even say like, well, this is quadratic, and then if I try to implement but what I would really like to do is implement a merge sort, which is, it's slower than linear, but it's better than quadratic. Yeah, because yeah, the worst case is that you try to write the optimal solution first, you mess up somewhere, and then you have to go all the way down to brute force, and you don't have time to finish, and you end up with two half finished solutions. So just do what you're comfortable with, whatever that might be. Okay, so those are different types of sorts. Um, the last thing I want to talk about, we're running out of time here, but I do want to cover the last thing that the course touched on. Well, there's two last things, but I'm going to hit one of them. Yeah, and exactly, piece of shoot. I love it. So this is what the instructor said too. Which is better, brute force, and you get the answer, or the most complex algorithm and it doesn't work. And the instructor said, yeah, sometimes what's most important is that you get a solution, right? You get a solution, something that you can deliver. And so that's kind of the philosophy we're going to take into this next topic that I want to cover before we end for today. Um, Talking about greedy algorithms. So, um, does anybody know what I mean when I say an algorithm is greedy? Even if you don't, you could probably take a guess as to what a greedy algorithm might do. What do we think those might be? What do we think a greedy algorithm might be like? Zach says it grabs all the best things first. Rascal says it doesn't tip. Um, but Maid says it uses a lot of space. Yeah, it uses a lot of resources, too much. Those are all great guesses. Yeah. So a greedy algorithm is going to make the best choice in its limited sphere of influence without considering the larger picture. And I have a better, that might not make sense right away, but I have a good visual example of that here in the next slide. So a greedy algorithm makes the choice that is optimal for it locally at that very moment. It's almost like a selfish algorithm, right? It says, this is what's best for me right now. I'm going to do it. I'm not going to look ahead. I'm not going to look behind, left or right. I see two options in front of me. I'm going to pick the one that is optimal in this moment without considering what might be two steps ahead, right? So it makes the choice that is optimal locally without considering the larger picture. So let's see what that looks like visually. All right, so here is an example of getting from point A to point G. And here we have a bunch of different points, a bunch of different paths our algorithm could follow. And since this is a greedy algorithm, it's only going to pick the optimal point locally at each step. So we start at point A. It sees there are two values, 5 and 3, and it wants to find the most efficient path. So the goal here is to find the most efficient path from point A to point G. So in this case, it's going to say, all right, this path is 5 miles long. This path is 3 miles long. Okay, 3. That's the most efficient from the options that I have. Okay, at the next stop, 4 miles long, 5 miles long, 6 miles long. 4. Obviously, that's correct. All right, next one. All right, 5, 6, and 2. 2 is obviously correct. Okay, next one is 5, 3, and 6. 3, that's the shortest. And then the next one, only one choice, which is 4. Now, looking at the big picture, this is obviously a terrible path, right? It is not the shortest path by any means. If we add up 3, 4, 2, 3, and 4, we get 16. So very much not the correct choice, but at each point, it was the correct choice locally within its limited sphere of view without looking forward or backward. That was the best choice. Yeah. So that's a good visualization of greedy algorithms. They are optimal locally. So with that, you might say, okay, well, that sucks. why would we ever use a greedy algorithm at all? Well, it's kind of like we come back to a lot of those trade offs, right? You could potentially, consider every future scenario and try to optimize in that way, looking as far ahead in the future as possible, looking at all the possible choices, all the possible configurations before and behind you. However, as the complexity of your excuse me, as the complexity of your data structures grows and the complexity of the calculations that you're doing grows, you might not be able to look all the way into the future and see if the choice that you are making now is the correct choice 20 steps down the line. That just may not be possible for you to do, or it may be incredibly resource intensive for you to do. So, when a data set or structure is so large that you can't think about every scenario and you just want it to work, so you just want it to function, return you a solution. Maybe this is the best choice. Yeah. So that's when we have a greedy algorithm. Um, okay, and then the last thing the course briefly touched on was dynamic programming, and this is more. So this is the last thing I want to talk about before we wrap up. So dynamic programming is another good vocab word to know. And in general, dynamic programming just deals with something we already talked about. So do you remember? Cast your mind back to let me see. Cast your mind back to these exercises that we did before, where we took some values, right, and we each time we encountered a new value that we hadn't seen before, we cached it. We dropped it into a cache and constructed our function in such a way that that cache persisted over multiple function calls, and we were able to return a value from that cache if we ever saw it again. Without going through all the mathematical calculations again, we were able to simply access the cache and return the value. Boop, no problem at all. Can this be optimized? Yeah, it absolutely can be optimized. Yeah, memoization. This function could 100% be optimized. This was more about just showing the concept of memoization. We did optimize it a little bit with Clojure. So we use Clojure here to put our cache into a limited scope that was still persisted but was accessible by the child. However, this concept of storing values for future use is kind of the definition of dynamic programming. And I love the instructor in the course says something like dynamic programming is like one of those buzzwords that they came up with because it sounds cool. It doesn't really describe what's happening. It's sort of like JavaScript isn't related to Java at all. It just sounded cool at the time. And so I don't know whether that's true or not. I haven't done my research, but so dynamic programming really just describes sort of this act of caching values to avoid repeated calculations. And so the main qualities of dynamic programming are that it has kind of an optimal substructure and overlapping sub problems. So when we talk about sub problems, we're just saying like, as we overlapping sub problems, we can find repeated values that we want to access again, find those in cache, and return them instead of performing the operation again. Sometimes our subproblems will overlap, and so we can share the results between those subproblems without recalculating every single time. Yeah. So the value persists after being returned. Yes. So we're caching that value so that we can return it again immediately without recalculating it every single time. We say, oh, okay, the answer to 9 times 10 is 90. All right, I'm going to keep that in mind. My code says I'm going to keep that in mind. I'm going to store that. And if I ever see the value of 9 passed in as something that they want multiplied by 10, instead of doing that again, I can just say, I already know the answer to that. I don't got to do that again. I'm just going to return the value I returned before. Yeah. Yeah, Zena. So this particular course doesn't really get into hash maps, but I believe yes, I believe that's the same concept. Yeah, I'm sure other folks that are more familiar with hash maps can answer that question as to the similarities and differences and all that. But yeah, this course I believe it's mentioned at some point in the course that they are a similar concept. Yeah. Okay. So those are the main points of what was touched on in this course. Again, please, please, please watch the course. Don't just listen to me. Um, I try to touch on things, like I said, I try to touch on things that are main concepts and or maybe were slightly glossed over. Um, yeah, we'll get to this week. Yeah, I figure the Primogen course is probably going to be more on that kind of thing. Um, so I look forward to it, but I don't. I'm the kind I don't really work ahead all that much when it comes to this type of theoretical stuff because I'll just burn out, right? I'll flame out like a jet engine. Figured that out in college. So yeah, I'm sure we'll get there, and I'm looking forward to it. That course is 9+ hours. Oh boy. Okay. Well, you're going to be getting some crazy Cliff's notes from me then. But yes, definitely please do the course. Look at the slides, and I'll link the slides again. Let's see. I'll link the slides again. I would highly suggest forking your own replets out of these slides. There they are again, and just messing with them. Put in console logs, change variables, mess with loops. See if you can optimize this code. See what it does. See if it behaves differently. Do what you can with it. Some good examples to start with. Go for it, Xena. Yeah. Okay. We do have a channel points reward to redeem. Somebody wanted to generate an AI generated image with a prompt of their choice. So Serious Scaper, are you still here? Let's check and make sure they're still around before we go into this. But yeah, for those of you who don't know, good. Oh, okay. So the prompt is Fantasy Forest, Lord of the Rings style huntress in silhouette. Ooh, fancy. Hey, Coding with Strangers. Welcome. Always good to see you, my friend. Yeah, so we're actually just wrapping up. But if you want to stick around, we're about to do an AI image generation with Stable Diffusion. So we went through all the boring stuff, all the talk about algorithms and big O notation and stuff. And now we get to do the fun part, which is an AI image generation that Seriescaper redeemed. And they gave us, oh, it's for a cover for a book. Oh, very cool. Okay, well, let's see what we get, huh? And so I'm going to pull this up. It still has the last thing that I generated on there, which is I was trying to make a joke at work about being like a fly in a business meeting. And so this is the last thing I generated. So sorry if you don't like bugs. I apologize. Um, I'm known to arrive and bring the fun. Yes, you are, Coding with Strangers. Go follow Coding with Strangers. They're super fun. I'll give them a quick shout out. They're super fun and wholesome and positive. There we go. Okay, so let me get your prompt again. Serious. Fantasy Forest, Lord of the Rings style huntress in silhouette. Yes. All right, Fantasy Forest, Lord of the Rings style huntress. All right, we'll see what we get. I'm gonna kind of leave. I don't really mess with the settings all that much. What this is, for those of you who don't know, you may have heard of Dolly or other AI image generators. And this is a similar one. It's an open source image generator, so you can download it yourself. You can I'm using a Stable Diffusion GUI, so you don't even have to implement it with the command line or anything like that. This is going to run locally on my machine. And yeah, so you can always look up the NMKD Stable Diffusion GUI if you want to try to run it yourself. You do need an NVIDIA graphics card on your machine. So that's the main qualification, and I think at least like four. There's some other qualifications too on their website, but yeah, NVIDIA graphics card is required. Okay, Fantasy Forest, Lord of the Rings style huntress in silhouette. Let's go ahead and generate. See what we get. And for any image that we generate, you can request that I send you those images. I'm happy to do it. I don't own these. They're the robot owns them. The AI owns them. They're not. I don't copyright them or anything like that. So I will send them to you on Discord if you want them. Any or all of them is fine. So it's running now. It generally takes a little bit longer than when I'm streaming because I'm using my graphics card to stream, and so the resources are divided. Don't give the robots the right to ownership. The machine owns it now. Yeah. That bug got 10 legs. Yeah. It's kind of wild the stuff that it comes up with. Teenage Mutant Ninja Flies. Yeah. It's public domain. Yeah. I don't know. There's all sorts of questions out there right now about who owns what AI creates, right? Because there are certain images that are used to train artificial intelligence. So where does the role of the original image creator come in? There's all sorts of questions. And I know that, traditional artists are concerned about this sort of thing, which is valid. Um, because at what point does their work become altered by still recognizable but altered by AI to the point where it's no longer theirs, even though they originally created it? I don't know. It's complex. All right, it's still loading. I'm gonna drag this halfway off the screen. You can still see it running. I'm gonna drag it halfway off the screen just because in previous streams, depending on the prompt, we've had questionable results come back sometimes. There's really no filters on the types of things you can get back. So I'm gonna drag that off screen until we start seeing what we get, and then I'll bring it back. GitHub Copilot is going through the same thing. People are saying it's copyrighted code. Interesting. Yeah. So if you don't know, GitHub Copilot is very similar to an image generator like Stable Diffusion. It uses AI to dynamically generate code while you type, but this code, obviously, any AI model has to be trained, right? And it's trained on real people, what real people have written in the past, or drawn in the past, or composed in the past. When it comes to music, and so what credit do they deserve? Yeah, and then there was an AI generated image that got first place in an art competition, and so there's lots of competing thoughts out there. Again, another Dylan Beatty lecture that I watched recently that I really enjoyed was called Computational Creativity, and he gives an interesting perspective on the role of AI in generating art. So it's on the NDC conference's YouTube channel. It's called Computational Creativity. It's a very interesting watch. It's about how computers have been used to facilitate creativity over the years. It's a tool, not a replacement. Yeah, that's interesting because the tools are going to continue to improve, right? So at some point, will they become a replacement? Maybe. Ooh, we're getting some good stuff back. Okay, I got to show you this. Oh, it's good. Oh, look at that. Look at that. That's rad. Remember the prompt was fantasy forest, Lord of the Rings style huntress in silhouette. Rascal's like, do we even need to see the rest? So cool. Yeah, it looks rad. And with just a little bit, maybe a little bit of touch up on the face, or you could even shadow out the face, and I think it would be perfect. Yeah. So we're still cooking. There's going to be five. It generates five total results. Generally, it goes faster. It takes a while to initialize, and then it gets a little faster as it goes. But I don't know. This might be the best one. Sometimes there's a big difference in quality between the various iterations, but yeah. And what this looks like to me is almost like a did anybody read the Abhorsen trilogy uh, by Garth Nix? So Sabriel, Lyriel, and Abhorsen, because those books. This looks like a lot like the cover of one of those books, like the original art, like the Sabriel book. Oh, that's another cool one. The horse leg looks a little weird. That's kind of creepy. It's interesting that that one's on a horse while this one is not. Yeah, in a different, like it's a different color palette too. Oh, I see serious. Okay, so good. She liked the first one. That's great. That's awesome. So I'm glad we've got at least one good one. I'm glad she liked it. Uncanny, yeah, it's a little uncanny valley. So all the silhouette on this one almost looks like one of those battle droids from Star Wars Episode One. You know, Roger, Roger. Remember the Roger, Roger droids? Yeah. Look at the head. Just kind of looks like. I used to love those droids. I had the Lego Technic set, which was like a giant one of those, and it would like fold up and spring out. I used to love those battle droids. Yeah, and if somebody has access to Dolly, you can enter the same prompt and see what you get. I actually have access to Dolly. We could run it in Dolly, um, and see what we get. No worries, Rezan. Thanks for coming. Oh, that's interesting. Wow, kind of like a misty forest, like someone wearing like one of those plague masks and stabbing. Like it looks like they have a torch and they're like stabbing a spear into the ground. Yeah, Dolly is pretty great. Yeah. I just wish you weren't limited. So the nice thing about Stable Diffusion on the Stable Diffusion GUI here is there's no limitations on how many times you can run it. With Dolly, you're limited by credits, or you have to pay for more time. Stable Diffusion is free as long as you have a machine that can run it. Um, Stable Diffusion doesn't cost anything. It's completely free and it's open source. So if you want to download it and do whatever you want with it, or you can train it for specific operations. I know that companies have taken Stable Diffusion and trained it for very specific use cases, like I don't know, identifying dogs or something like that. You know, they can train it specifically for that. Looks like Bridge to Terabithia. Yeah. Opinions on the Disney Star Wars trilogy films? I like Ray. I actually have a Ray outfit in my closet. I feel like I resemble her, so it's a good cosplay. Um, I didn't I didn't see the most recent the end of that trilogy. Actually, never saw it. Oh, serious? Are you seeing this? Look at that one. Friggin' a. That one wins. That is a pretty good one, I gotta say, because like she's like looking off to the side and she's got her like spear. Ah, so Mrs. Sirius apparently says yes, 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 yes. I really like that one. Awesome. I will. I'll send you all of these, and you can look at them closer and make your determination. Yeah. How often do I go live? Kim, on my Twitch homepage, which I assume where you are now, you can see click on the schedule tab and you'll see my schedule. I stream twice a week, generally Wednesdays and Fridays. So Wednesdays are 7 p.m. Eastern, and sorry, not Fridays, sorry, Wednesdays and Sundays. My bad. Wednesdays are 7 p.m. Eastern. Sundays are around 3 to 4 p.m. It really depends. I wait until a previous streamer stops going live, so I wait until they're done and then I go live. So it can depend on when they end. So the 100 devs, the head of 100 devs, Leon Noel, they can have streams of varying lengths sometimes. So anyway, it's around. You can look at my schedule on my Twitch homepage and you'll kind of see the general schedule there. Oh, that's a good one too. Ooh, it's going to be hard to choose, but that's not my problem. The Sirius family has to make that decision. And the question was, are you wearing your Ray costume to your Halloween stream? I do have a costume that's on the way. Um, it's not here yet. I think it's in Kentucky now. It's being delivered, so I'm hoping it gets here in time because that's what I was planning to wear at least for part of a stream at some point near the Halloween time. I'm not going to tell you what it is. I'm hoping it turns out okay. But yeah, so I do have a costume. Really hard to choose. Definitely a great proof of concept. Yeah. Yep. And each of these are going to need touching up. They might be the wrong size. Unfortunately, just resource limitations. They are limited in size to 512 by 512. I've tried making bigger results, and that just usually causes this to crash. So it's kind of unstable. So yeah, bigger images generally cause this to crash, but hopefully this can give you, a good starter to. I still think this one is the best. A good starter to get something good that you can use. Oh, that's still good though. Yeah, I'll send you all of these series, and you can use it to your um, to your pleasure, whatever you'd like. Is Leon Noel supposed to be a palindrome? As far as I understand, that's Leon's actual name. So it is. It happens to be a palindrome, unless he's got a pseudonym thing going on. I don't know, but yes, it is a palindrome by coincidence. Yeah, allegedly, right? I mean, we don't know. Heck. All right. This was awesome. Great way to end the stream. Thank you so much for claiming this reward. They're serious. Um, yeah, 100%. Let me get that Discord name so I don't lose it. Crichton 4518. Got you. I'm going to drop it in a Notepad++ here. Also, too, if you're not using Notepad++ as your text editor, do that. All right. Any last questions? We're going to find somebody. Otherwise, we're going to find somebody to raid and spread the love a little bit. We got a lot of folks still on stream, so we're going to raid somebody else. Vim gang, to each their own. Oh, and Rascal did a Dolly prompt. Okay, let's see that. Okay, so this is the output from the same prompt for Dolly. Yeah, and I can send you these as well, Sirius. So you'll have a bunch to choose from. And these are good too. Very similar, and it's interesting. These are more like cartoony style, right? Like a little bit more, yeah, cartoony versus the atmospheric style of the ones that Stable Diffusion generated. So it's interesting. Yeah, 2 is good. The face is a little dodgy, but faces tend to be dodgy in AI so far. It doesn't know what we look like. It doesn't understand faces. Yeah, all of these are good too. I love all of these. So yeah, I will send all of them to you, Sirius. So you'll have all of them. Okay, let's look up a raid target, but feel free to ask any remaining questions that you might have about anything. Doesn't have to be about data structures and algorithms. Whatever you want to ask about, happy to answer while I find someone to raid. All right. Seems each batch gave me 1 human and 2 or 3 silos. That's interesting. Raid. Okay. Is Digilstra something you covered today? Leon will cover. No, we didn't cover that today. We covered a specific course called from Front End Masters called Practical Algorithms. I don't know what Leon is going to cover going forward. Yeah, I'm not sure. Well, we didn't really. So if that's a greedy okay, so I didn't know what that was actually. Thank you for that. That's a greedy algo. We talked about what greedy algorithms are, from a vocabulary standpoint, but we really didn't look at any of them specifically. There are a few greedy algorithms examples that are shown in the course material. But yeah, we didn't really have time to dive into those today. So I see we've got a few raid targets here. We've got CM Griffin, Team Vash, and Dion Saga. All 3 of them are doing software and game development. If anybody has any other people that they'd like to raid, do let me know. Well, if you optimize that greedy algorithm, then it's really not greedy anymore. I would think so. Well, if you optimize it to look at the big picture, then it's no longer greedy, right? When is a greedy algorithm not greedy? All right. So CM Griffin, Team Vash, or Dion Saga. But does anybody have any other people that they would like to raid instead? Yeah, piece of shoe. They're optimized for best path though, just the immediate one, right? If at any point you expand that scope to think about the bigger picture, then it's no longer greedy because it's looking at other options. It's looking into the future, right? Oh yeah, Purple Elf. Yeah, we haven't hit them in a while. Are they on? Purple Elf. Oh yeah, they are. Okay, yeah, let's do Purple Elf. I don't know why didn't they show up? I thought I was following them. So let's raid Purple Elf mostly so I can follow them and correct that oversight. Yeah, Purple Elf is fun. All right, we're gonna go ahead and raid them. So I'm starting the raid now. I will see you all again for class on Tuesday with Leon. So again, exclamation! If you're not sure what I'm talking about, exclamation point Leon. Join our Discord. Look at Leon's Twitch, and then I will be streaming again on Wednesday for my regularly scheduled stream. Thank you all for joining me today. Had a lot of fun, and go do that front end master's course. Don't rely on me. All right, I'll see you all again soon. Raid is starting. All right. I hope that everyone has a great rest of your Sunday and a great start to the week. Okay, here we go. Rating now.